We have spacecraft separation and confirmation from our video system.
Approximately 50 minutes after launch, the spacecraft separates from the upper stage of the launch vehicle. 6 minutes after that, the spacecraft transmitter sends a signal back to Earth, which is received by the tracking stations. Once we receive that signal, we're ready to send our first command up to the spacecraft, and that actually marks the beginning of the cruise phase.
There are some incredible challenges on the way to Mars. One of the things is there are always anomalies. There are always things that are going to go wrong that you never expected. You have a baby spacecraft that is now on its way to Mars, and it's seeing the space environment for the first time. So it's going to see temperature ranges from minus 250 degrees Fahrenheit to plus 250 degrees Fahrenheit. And you've got instruments all over the spacecraft. You've got propellant lines that you can't let freeze. And so there's always this challenge of keeping the entire spacecraft tuned thermally.
Some of the things that we're going to be doing during the cruise phase are some trajectory correction maneuvers, which are basically pushing us along the path of where we want to end up when we arrive at Mars. The launch vehicle puts us at a specific path on a trajectory, and along the way from here to Mars, over the 9 months that we're going to be flying there, we need to make small corrections to that.
If you were trying to shoot a bow and arrow at a bullseye, at a target, and you had drawn back the bow and you had shot off the arrow, and you realized all of a sudden that it wasn't actually going to hit the target, how great would it be if you could pause in the middle, make a slight adjustment to the arrow, and watch it hit the target?
We have given ourselves 6 opportunities to make a trajectory correction maneuver. And each of those correction maneuvers uses the thrusters on the spacecraft to give a little push to the spacecraft to correct its trajectory.
One of the things that makes landing on another planet so difficult is that we're essentially trying to hit a moving target. The spacecraft left a planet that was spinning around the sun at its own speed, and we're now aiming for another planet. And we can't just aim for where the planet is at the time that we launch, but we have to aim for where we think the planet's going to be by the time that we get there.
All of those motions, the navigation team has to carefully track and predict where things are going to be in the solar system in order for us to successfully navigate to Mars.
The trip from here to Mars is over 8.5 months, and we need to make sure that we monitor all the sensitive instruments, science and engineering, to make sure that over the 8.5-month journey, everything is working properly.
The better we do our jobs during the cruise phase of the mission, the better the entry, descent, and landing phase of the mission will go, as well as the surface phase.
And liftoff of the Atlas V with Curiosity.
NASA's car-sized Curiosity rover may be on cruise control to Mars, but that doesn't mean it's not working hard along the 8-month-long trip. The Mars Science Laboratory rover is busy monitoring space radiation with its Radiation Assessment Detector, or RAD. The instrument detects high-energy atomic and subatomic particles from the sun, distant supernovas, and other sources that might impact humans on future long-duration spaceflights.
So measuring the radiation environment in space is not new, but what is new is that RAD will measure for the first time the radiation environment inside the spacecraft, which will be very similar to the environment that a future astronaut will see inside their spacecraft on a future mission to Mars.
At least one object rover Curiosity is slated to photograph on Mars later this year will be immediately recognizable to most, if not all, Americans: a Lincoln penny. This 1-cent piece, struck in 1909 when the coin was first issued to commemorate Lincoln's 100th birthday, is on a smartphone-sized plaque attached to the rover. When the Mars Science Laboratory lands in early August, a camera at the end of the rover's robotic arm will use the penny to help its calibration. The Mars Hand Lens Imager, or MOLLE, will show details of Martian rocks and soil so tiny that the calibration target includes reference lines finer than a human hair.
We can position a camera up next to a rock or some soil, and we can take pictures of it like close up, or we can pull it back and we can take pictures of a broader scene, the landscape. We can even look back down on the rover itself.
Curiosity also carries 4 other science cameras, a dozen black and white engineering cameras, and other research instruments. MSL will deliver Curiosity to a landing site on Mars known as Gale Crater, where the rover will conduct a 2-year investigation of whether that area of the red planet may have ever sustained microbial life.
A rocket sled that replicates the forces a supersonic spacecraft would experience prior to landing was recently tested by NASA at the U.S. Naval Air Weapons Station at China Lake, California. Sleds like this will allow the Low-Density Supersonic Decelerator Project, or LDSD, to test inflatable and parachute decelerators for slowing spacecraft as they descend on Mars and other destinations. That would enable NASA to increase the size of payloads it lands and landing accuracy. These new decelerators represent the first steps on the technology pathway to land humans and habitats on new worlds. This test series is led by the Jet Propulsion Laboratory. LDSD is one of 9 missions managed by NASA's Marshall Space Flight Center on behalf of the agency.
Representatives from the Ames Research Center and the National Park Service gave the public an up-close look at how the extreme conditions of California's Death Valley are helping NASA prepare for surface exploration of Mars. The first ever Mars and the Mojave Festival featured geology and mini rover demonstrations, a scale model of the Mars Science Laboratory's Curiosity rover, and guided tours of areas whose topography and characteristics make them ideal research sites for equipment testing and evaluation in a Mars-like environment. Among these sites is Badwater Basin, the lowest point in the continental United States, where specially adapted microbial life can be found under salt and mineral deposits. Mars Hill, which mimics the boulder-strewn Martian surface first seen up close by NASA's Viking landers, and Ubehebe Crater, where scientists can plan crater exploration for missions like MSL. Researchers with the Mars Science Laboratory project at the Jet Propulsion Laboratory recently took science journalists on a 2-day field trip and workshop to California's Mojave Desert.
Oh, it's beautiful. Isn't it great?
The journalists were shown sedimentary rock exposures that, like those the Curiosity rover will study on Mars, reveal to scientists the history of their environment.
The hard part is how to extract the information from the rock. So that's what everybody's learning to do here, is how to make measurements. We measure the thickness of the beds, we measure their grain size, we look at their mineralogy as best as we can understand it, and we record all of this information, and then from that it will eventually allow us to reconstruct what kind of environment was here.
Liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
The MSL spacecraft carrying Curiosity was launched November 26, 2011, and is scheduled for an August landing on Mars at a site known as Gale Crater.
I'm Alan Chen. I'm the operations lead on the Intercept and Landing team for the Mars Science Laboratory project. Right now, I'm coordinating our preparations for entry, descent, and landing. We land in August, a few months from now, and we're still hurrying to get all our stuff ready to make sure that we're ready to take the plunge. I'll be telling people exactly what the spacecraft is doing, roughly where it is, and what it's telling us is going on during EDL. My parents always displayed an example that education never stops. You always want to learn as much as you can, and it doesn't stop when you leave the classroom. My parents added new skills while I was still in high school, and they got other degrees, and a lot of the times it was just for fun. We have essentially a copy of the spacecraft over in a different building here, where we can try to get this virtual spacecraft to run through the motions it will go through during EDL. We run trajectory simulations to understand its performance. We've probably literally run millions of simulated cases from cruise stage separation all the way to the ground to make sure we get where we're going. You gotta work hard. There's a lot of academics that you need to get to this point in your career. Beyond that, I would also emphasize that it's not just about science and math per se. If you can't talk about what you're doing, you're not going to get very far in this. You're going to have to convince people. This is a type of mission and a type of project and a type of thing that we do here that no one person can do by themselves. So you got to work with a lot of people. And learning how to work with those people is just as important as learning those basics in science and math. That's kind of the starting point, but to grow beyond that, you need to be able to work with people. There's a kind of exploration that we do here that can't be done anywhere else. There's certainly other places where you're doing things to make money, or you're doing things related to exploration, but here, the entire point of the place is about exploration. So I think I finally came to that realization sometime in late high school or early college that this is the type of place I want to be at.
NASA has narrowed the landing target for its most advanced Mars rover, Curiosity. When it sits down on the red planet in August, the car-sized rover will now be closer to Gale Crater's Mount Sharp, where it'll conduct its science. Fear of any additional risk that comes with putting down nearer the mountain's hazardous slope was overcome by confidence in Curiosity's precision landing technology. Rock layers located in the mountain are the prime location for rover research. Launched in November 2011, Curiosity is scheduled to land at approximately 1:31 a.m. Eastern Daylight Time on August 6th. Following checkout operations, Curiosity will begin a 2-year study of whether the landing vicinity ever offered an environment favorable for microbial life.
15 years ago, on July 4th, 1997, the Mars Pathfinder landed on the Red Planet 7 months after it was launched. Pathfinder landed on Mars's Ares Vallis in a region called Chrysi Planitia in the Oxia Palus Quadrangle. The mission carried a series of scientific instruments to analyze the Martian surface, climate, geology, and the composition of its rocks and soil. It was the second project from NASA's Discovery program. Pathfinder consisted of a lander renamed the Carl Sagan Memorial Station and a lightweight robotic rover named Sojourner. In addition to scientific objectives, the mission was also proof of concept for various technologies, such as the airbag-mediated touchdown and automated obstacle avoidance, both later used by the Mars exploration rovers.
Spektakuläre Aufnahmen. Die US-Raumfahrtbehörde NASA hat ein riesiges Panoramabild vom Mars veröffentlicht. Das Foto ist zusammengesetzt aus 817 Einzelbildern, die der NASA-Rover Opportunity geschossen hat. Einzelne Fotos zeigen zudem den größten Krater, den die NASA bislang erkundet hat. Wissenschaftler gehen davon aus, dass er vor 4 Milliarden Jahren entstand.
When the Curiosity rover sets off from its landing site near Gale Crater to explore the Martian surface, the Mobile Science Laboratory might encounter some sand dunes. Project engineers at the Jet Propulsion Laboratory have prepared for that possibility by putting a test rover through the paces here on Earth.
Through careful targeting, we've been able to shrink the landing ellipse for Curiosity, and we've been able to move it closer to where we want to actually land. In case we land in dunes that are like this on Mars, near the landing site, we want to be sure that the real rover is able to navigate around successfully in those dunes and get from the point where we landed to the point where we really want to be. So we've come out here today with the Curiosity Scarecrow rover, which is the same weight on Earth as the real rover is on Mars, to practice driving it around in the nearest thing to those dunes on Mars that we're going to find here on Earth. This is similar material and similar slopes to the dunes that we're going to find in Mars. So being able to test this rover in these dunes gives us a good idea about what the performance of the real rover is going to be in the dunes that we might land in on Mars.
Still making progress.
The performance on this rover is actually fairly similar to Spirit and Opportunity. A little bit better. We can climb in soft sand up to about 15 degrees or so, which is a little better than Spirit and Opportunity will do. We are in fact right now maneuvering it from an area of about 15 degrees of tilt to an area of about 25 degrees of tilt to try to explore where that break is in its performance. Our top speed is very slow, but our acceleration of that top speed is pretty much instantaneous. So we go from a dead stop to right about as fast as we're going to go pretty quickly. It's really fun to, like, every once in a while, kind of leave the office environment behind and come out to an environment like this and see what the real rovers are going to be doing on Mars. It kind of connects you to it and reminds you that, that the computer models that we play in are a far cry from reality. This is that reality.
When rovers land on Mars, they travel all the way to the red planet protected by a rigid aeroshell, or heat shield. The size of that structure limits just how much scientists and engineers can fit inside.
If you look at all the origami that's involved in packing a rover, like we're sending to Mars right now, into that confined space, and then having it deploy in the right sequence during that timeline when you've only got a certain amount of time to do it, it's very complicated.
So Neil Cheatwood and his colleagues at NASA's Langley Research Center in Hampton, Virginia, have come up with a different idea. an inflatable heat shield. The first flight demonstration of the concept is the Inflatable Reentry Vehicle Experiment, or IRVE. The launch of the 10-foot diameter mushroom-shaped IRVE-3, which is packed uninflated into a 22-inch diameter rocket, is currently scheduled for mid to late July.
We will launch IRVE-3 on a sounding rocket out of Wallops Island. It will go up into space, inflate to reentry shape, and perform its reentry experiment, and it will radio the data back home. When the experiment is over, IRVE-3 will land out in the Atlantic.
IRVE-3 has been tested and retested on the ground to make sure it can withstand the heat and force of atmospheric reentry. The first line of defense against those conditions, the thermal blanket, is made up of layers of commercially available materials.
This combination includes Nextel, which is an aircraft engine insulator. We use Pyrogel, which is a pipe insulation material. And then we use Kapton-coated Kevlar. Kevlar is the same stuff that police use in bulletproof vests.
IRVE has already had one successful test. Assuming IRVE-3 does as well, engineers hope to expand the concept, literally, and test a larger inflatable in the future.
The Curiosity rover continues to make its way to Mars, and its scheduled landing in Gale Crater on Monday, August 6th at around 1:30 in the morning Eastern. Once delivered to the red planet's surface, Curiosity will begin a 2-year prime mission to investigate one of the most intriguing places on Mars. Join NASA TV coverage of Curiosity's landing on Sunday, August 5th at 11:30 p.m. Eastern. We'll have it on all 3 NASA TV channels, on nasa.gov, and on Xbox 360 as well.
While the real Curiosity rover makes its way to the red planet, reporters on Earth met the rover's stunt doubles in the JPL Mars yard.
We've had a rare moment where between testing, where we can invite people over and actually watch us do some testing.
The vehicle system testbed, the VSTB rover, is essentially Curiosity's twin sister, where it's almost the same as the rover that's about to touch down on Mars. And we're testing autonomous navigation software today. So what we're doing is we're setting up a pile of rocks. The rover is imaging the world around it, and it's determining where is it safe to drive and where is it not to.
Media visitors saw the rovers in action and talked to scientists, rover drivers, and engineers. Landing day is on everyone's mind. It's coming up fast.
You have to be nervous. I mean, it's a very difficult thing to get right. But, you know, the thing is, we have done all the testing we could think of, and we put the effort in, and I'm very proud of the team.
Curiosity is not a life detection mission. We're not actually looking for life. We don't have the ability to detect life if it was there. What we are looking for is the ingredients of life.
The Mars Science Laboratory takes this Curiosity rover with this incredible set of payload instruments to figure out if Mars ever could have supported microbial life.
By that we mean a place where microorganisms, little tiny single-celled organisms, could have lived, and that requires a source of energy and water, because all life as we know it is associated with water, and then we also need a source of carbon.
Curiosity is going to land at Gale Crater. We're going to be climbing a mountain. In fact, one of the first things we'll see when we wake up the first day on Mars is this giant mountain in front of us, just waiting for us a few miles away.
And in that mountain, there's a stack of layers, and like turning the pages in a book, we will explore these layers and look at them in terms of whether or not they preserve evidence for ancient habitable environments.
So you can think of Spirit and Opportunity as robotic geologists. Curiosity goes one step further. It's not only a robotic geologist, but a robotic geochemist.
We need a bigger rover this time around because we've got 10 science instruments, and 2 of them fit inside of the belly of the rover.
We bring some state-of-the-art laboratories to do very detailed geochemical analysis of the rocks and soils on Mars, and the atmosphere as well. We have to feed those instruments by getting samples of rock with a big robotic arm and a drill on the end of it. And then we, of course, want to have all of our eyes and the other senses that we need with cameras and other detectors to monitor the weather and other things as well.
The reason it's important to have this capability is this brings us back to how we address the question and search for habitable environments again. We need to make those measurements in order to know that if life had evolved on Mars, would this be the kind of place where microorganisms could have lived?
Right now, NASA's Curiosity rover is closing in on Mars. After 8 months of hurtling through space, it is set to land on the red planet in less than 3 days. The U.S. Space Agency is bracing for a bumpy ride. Its explanation of the landing, it kind of feels like a movie trailer. Let's check it out.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
Well, gripping stuff there, but the odds are not on NASA's side. The red planet has a track record of rough landings. Roughly 60% of missions to Mars have failed, and Curiosity cannot simply land on the planet. It will take a supersonic parachute, a retro rocket pack, and a long tether to set the rover down gently. So, if Curiosity makes it, what will it do? Well, it's considered the first roving lab ever to be sent to another planet, and it's looking for signs that life existed on Mars. It has a high-tech toolkit with cameras, a robotic arm, a laser. It can also drill rocks and sniff out organic materials like carbon, the building block of life. Now, it is much bigger than the previous rovers, about the size of a small car, like a Mini Cooper. It's also 4 times heavier than other rovers. Now, it runs on a nuclear-powered battery that should last a full Mars year, or about 687 Earth days. Now, scientists are hoping that it could run for much longer. And NASA Administrator Charles Bolden tells us more about the mission.
If you can imagine going into the Grand Canyon, where we can look at the history of Earth, really, in that area as we look at various strata, that's what landing in the crater allows us to do. And it's actually going to climb the mountain, so it will look across the geologic history of the planet Mars in the 2 years that it's there. It's a harrowing experience. It's, as they say, 7 minutes of terror, but that's why we are NASA, because we like to do things like that. We love risky things, but we're confident.
Now, here's hoping that luck is on NASA's side. And that is Newsstream, but the news continues at CNN. World Business Today is next.
Good morning and welcome to NASA's Jet Propulsion Laboratory. Today is L-1, that's landing day -1, and everyone is getting more and more excited as we get closer to the landing of the Mars Curiosity rover tomorrow at 10:31 p.m. Pacific time. I'm going to introduce our panel from the mission team. They're going to explain a little bit more about what to expect tomorrow night, and we'll start with Doug McQuistion. He's from NASA headquarters, and he is the Mars Exploration Program Director. Arthur Amador from the Jet Propulsion Laboratory. He is the mission manager for the Mars Science Laboratory. Steve Sell, also from JPL. He is on the entry, descent, and landing team. Richard Cook from the Jet Propulsion Laboratory. He's the Deputy Project Manager of the mission. And Ashwin Vasavada, also from JPL, the MSL Deputy Project Scientist. And we'll begin with Doug McQuistion.
Thank you, Veronica. 1 day, 12 hours, 59 minutes, 45 seconds. Who's counting? Anyway, it gets scarier every day. So I want to start actually with something a little different here this morning. I'm going to start with what's going on with the orbiters. So Odyssey's in good shape. I mentioned at a press conference 2 days ago that it was now in position to collect the telemetry and beam it back to us in a bent pipe mode. MRO started its EDL sequence yesterday. And what I want to show is a quick animation of what at least MRO is going to go through to cover the MSL entry. So if we can bring this first animation up. What you're seeing is video imaging of MRO. The red vector is the -X of the spacecraft. What's important is the green vector, which is the pointing angle of the high-rise imager. And you'll notice the spacecraft flops around quite a bit. This is both to keep the sun in line as well as pointing down. You see MSL coming in the pink as it lands, and we're going to attempt to have high-rise point at MSL in its final phases of descent and get an image of it going down. This is going to be difficult. As you can see, the spacecraft does a lot of gyrating related to gymnastics, if you will, since we're in the Olympic season. But it's a pretty challenging thing that it's doing. The team's worked really hard, and the Odyssey team has worked equally hard on their system. So these guys and gals and their spacecraft are ready to do this. And I really hope we can get this image, but it's going to be tough. We were really lucky on Phoenix getting that one. We'll see if we do it this time. So that's kind of a fun video. Back to MSL. Like all missions, MSL started with something that was pretty scary and pretty risky, and that was called launch. Unlike most missions, we haven't finished the scary and risky stuff yet. MSL still has to put Curiosity on the surface after it goes through the atmosphere. Our 7 minutes of terror, which you'll continue to hear about. So can we do this? Yeah, I think we can do this. I'm confident. The team's done an amazing job. We have the A+ team on this. They've done everything possible to ensure success, but that risk still exists. It's going to be tough. If we're not successful, we're going to learn. We're going to learn from this. We've learned in the past. We've recovered from it. We'll pick ourselves up. We'll dust ourselves off. We'll look at this and do something again. We'll do it again. This will not be the end. Human spirit gets driven by these kinds of challenges, and these are the kind of challenges that force us, drive us to explore our surroundings and understand what's out there, and obviously look at why are we alone. Let's bring up this next graphic. But to tell you how hard this is the scoreboard. We are behind. Mars has been winning. The global success rate is about 40%. This is orbiters, landers, flybys, etc. So it's tough. This is the most challenging landing we've ever attempted. So we'll see how this goes. We're all looking forward to it. I'm confident. I'm proud of this team and what they've done, and I'm proud of their readiness. It's pretty exciting. So at the end of this little talk on Phoenix, I quoted a Rolling Stones item. So to continue that tradition at this point, I'm using Tom Petty today. So we're learning to fly and we don't have wings. Getting down is the hardest thing. With that, over to Arthur.
No problem. Okay. My name is Arthur Amador. I'm the MSL Cruise EDL Mission Manager, and I'll give a quick summary of our current status, recent events, and upcoming operational activities. So regarding our current status, we're at entry minus 36 hours. The spacecraft and ground systems are all healthy and performing as expected. The spacecraft is now in the EDL approach configuration. In our final approach orientation, pointing our medium gain antenna within a degree of the Earth, we've got a strong telecom signal receiving data at 2,000 bits per second over the DSN antennas of Madrid as we speak. The power subsystem is healthy. Our rover batteries are charged to 100%. The thermal and propulsion systems are nominal with stable temperatures and pressures. And the DSN continues to perform well, tracking the spacecraft continuously and conducting 2 differential ranging passes per day. Can I get the graphic, please? So with a little under 4.5 million kilometers to go to reach Mars, we've traveled now 560 million kilometers around the sun since launch 8 months ago. And we're now right on target to fly through the eye of the needle. That is our target at the top of the Mars atmosphere. The target is a box that's 3 kilometers by 12 kilometers in dimension. And we're flying right through it. Okay, thank you for that graphic. Events over the last few days on the spacecraft have been nominal and quiet, as nominal and quiet as we could have hoped for. The spacecraft has been under the autonomous control of the onboard EDL sequence since Monday evening and has been executing its actions as planned. Our trajectory inbound to Mars has been right down the pipe, so we canceled last night's opportunity to perform our 5th trajectory correction maneuver. During the hours that we have left here before landing, the flight team will remain vigilant, monitoring and assessing the health of the spacecraft and tracking its trajectory and preparing any necessary changes to guidance and entry parameters. We have several opportunities to make final parameter updates, one today and 2 additional opportunities tomorrow if we need them. We have one more significant activity to perform with the spacecraft late tonight, and that's to command the final enable and activation of the contingency software on our backup computer. The team's confident and thrilled to be finally arriving at Mars. And we're reminding ourselves to breathe every so often. Our system's in place, and we're ready to go. So I'll pass it on to Steve Sell and the EDL team.
Good morning. My name is Steve Sell. I'm on the entry, descent, and landing team here at JPL for Curiosity, and like Arthur, I just have to keep reminding myself to keep breathing. Only got 36 more hours to go. And so I just want to walk everyone through what we can expect to see and hear tomorrow night as we go through entry, descent, and landing. As you remember, because we've probably been talking about this for quite a bit over the past few days, there's several different phases of EDL. And at first we enter the Mars atmosphere. We're going about 13,000 miles an hour when we do that. And as we slow down with the initial drag on the atmosphere, that's what we call the entry phase. And during that time, we're doing our hypersonic guidance maneuvering. So we're basically carving back and forth through the atmosphere to control how fast we're slowing down, to get ready to deploy the parachute at about 1,000 miles an hour, and then we're on the parachute for a while until we get a good radar solution on the ground. Once we get that radar solution on the ground, we wait until we're about a mile off the ground, and then we cut free from the parachute, do our powered descent, and finally ending in the wonderful sky crane maneuver where we lower the rover on 3 bridles underneath the descent stage and set it gently on the ground, and the descent stage then flies away to a safe landing about 500 meters or so from where we place the rover. So, like you all, I'm going to be, eyes peeled to the monitors for this whole thing, and so I just want to tell you how we're going to be watching this. And we actually have 4 different ways that signals are coming back to Earth, and so there's a lot going on here. I'll try my best to explain it pretty clearly. Just thought at first I would point to some things on the spacecraft here that are of interest for the communications during entry, descent, and landing. The first is this antenna that's tilted out the side of the parachute cone here. That antenna will be transmitting on the X-band, and I'll get into that in a little bit, but that will be transmitting tones back to Earth, and we've used those in the past in past missions. And there's an antenna that wraps all around the parachute cone here, and that will be transmitting on the UHF frequency, and that will be transmitting data back to Earth, or to the relay orbiters that Doug mentioned before. So the tones are basically a series of beeps from the spacecraft. We don't actually hear them as tones in the control room. We actually just see them appear as numbers on the screen, but there's no actual information or data transferred in those tones. They're just markers of I've gotten this far in the entry, descent, and landing sequence. The UHF is a more rich data set. Then we can actually send numbers back, so we get things like altitudes and velocities, positions, and more rich data like that. So how this will play out on EDL night, tomorrow night, we actually have a unique timing where we've tweaked the orbits of the Odyssey spacecraft and the Mars Reconnaissance Orbiter so that they will pass over the landing site as we're landing there, and we'll use both of those to relay our UHF data back at different timescales, and I'll get into that in a second. But if we could bring up the first video, it demonstrates the sequence of events as we're approaching Mars. You can see MSL there with its leaving a little trail as it's coming in. So Gale Crater appears on the right of the screen. You'll see it marked there. So this is coming in from the west to the east, and you'll see MRO will pass over the landing site from the south to the north, and you'll see Odyssey come in from the north to the south. You'll see it in a second, and MSL is just about landing. It touches down almost when MRO is directly overhead, and Odyssey is passing off a little bit more to the east. So that's the timing that we're using to cover entry, descent, and landing. And the way we're using both of those spacecraft is Odyssey is operating in what we call a bent pipe mode, which allows us to relay data back to Earth in real time. So that's what we're going to be glued to on the computer screens. Everybody's going to be watching that, and we're using that to drive some pretty cool animations that will show the telemetry in graphical form as it comes back. So you'll actually see pictures of the capsule and the parachute and stuff like that, and we'll actually be able to watch the telemetry in a meaningful way as it's descending. The tones actually will start transmitting those about 10 minutes before entry into the atmosphere, and those tones are direct to Earth, so they do not get relayed through the orbiter. The tones will keep being emitted by the spacecraft all the way down to until we're on the parachute. At that point, the Earth actually sets from view of the spacecraft, and so we will no longer be able to receive the tones. Although the spacecraft will still be sending them, we're kind of blocked from view. However, Odyssey passing overhead will still continue to relay that high rich data set back to Earth all the way through touchdown and for a few minutes after touchdown. In addition to the tones and MRO and Odyssey, we will also be making use of the European Mars Express spacecraft, which will be recording the UHF signal, and it will send what it hears back to Earth several hours after landing. And I know there's a lot of stuff going on here, so we put together a little video to try to help explain the sequence of the different timings. So if we can have the second video, please. You'll see the spacecraft entering there, emitting the Aquaman UHF tones and the little magenta or pink the pink tones, they're direct to Earth. And you can see MRO and Odyssey passing over the capsule as it's landing, and when Odyssey gets into view of the UHF, it then relays that back to Earth. And MRO will record that UHF data and play it back a couple hours after landing. And there you see the DSN receiving that information for us to view here at JPL. And so, as I said, we expect to have the Odyssey bent pipe relay to us all the way through touchdown, through several minutes after touchdown. And then at approximately an hour and a half after landing, Odyssey will replay that data again back to Earth, everything it heard, just as another way of getting the data back again. MRO will replay what it heard back to Earth, and that replay will start that replay will happen several hours after landing, and the data will actually be available to us. We have to go through a slight decoding process once we get that data down, but we'll have that about 10 hours after landing. And I have to say that I'm extremely excited to be watching all of this through whatever data we get on the screens here, and I can't wait for all of us to see it happen tomorrow night. And with that, I'll turn it over to Richard, who will walk you through what's happening after touchdown.
Okay, well, good morning, everybody. I'm Richard Cook. I'm the Deputy Project Manager. I like the tractor beams in the video. That was cool. So I'm actually going to talk about what occurs after landing. And of course, the big difference between cruise, as we are right now, and once we land, is that our ability to communicate with the vehicle and to see what it's doing all the time changes. We can do that during cruise because we have, at this point, continuous deep space network tracking, but once we're on the surface, it changes pretty dramatically. Part of that's because, to be honest, we don't know exactly, well, Steve told you what the plan is for landing, for communications. Clearly, there are situations that will occur or potentially may occur during EDL where we won't be able to get that communications all the way down. Some of them we know about when the vehicle separates, for example, the rover separates from the descent stage. But in addition, there certainly are situations that might come up where we will not get communications all the way through. And it doesn't necessarily mean that something bad has happened. It just means that we'll have to wait and hear from the vehicle later when it gets opportunities to communicate with us in the subsequent day or hours and days following that. So what I'm going to talk to you about first is really those communications opportunities that occur right after landing and what we expect to see during those opportunities. So if we start with the first slide, And I have to show view graphs because I'm an engineer, I guess, and so here's my view graphs on what we expect to see in terms of communications opportunities on August the 6th, clearly after we land late at night on the 5th. The first opportunity for hearing from the vehicle is the one that Steve referred to, which is actually during the landing itself. And we do expect Odyssey to remain visible from the rover from anywhere between 2 and 5 minutes after landing. And during that time, we should get some engineering data. We hope to get an indication that the spacecraft transition mode into what we call the surface mode, out of EDL into surface mode. And it's possible we also might get some images as well, and I'll come back and talk to you about that in a second. But because of the geometry that Odyssey is in, you saw from the video where it flies over kind of off to one side of the rover, it turns out we actually have a separate Odyssey opportunity later, about 2 hours later that night. And so it's at 12:30 in the morning is when we expect to get that second pass. It'll again be about a 9 or 10 minute overflight. And hopefully by that point we are essentially done with all of the first set of activities we wanted to do on the first day of after landing. It's we land basically at about 3:30 on Mars, and so this rover has another hour, an hour and a half of activity to do, and then the Odyssey overflight will occur, and we'll basically be done with the things we expect to do. That Odyssey overflight will be the next opportunity to get some pictures back. And again, I'll talk a little bit more about this in a bit, but we are in both of these two overflights that late morning, or late evening rather, early morning, we expect that we might get some black and white fisheye lens HazCam images. And I do have the rover here in case you guys are wondering what cameras we're going to be taking pictures of. They're from the HazCams that are on the back of the vehicle here, and they are black and white. We might get, they have covers on them, and so we might actually get images from the first pass and right after landing through those covers. The covers are actually transparent, but then we'll actually deploy those covers and we'll take some more pictures, and so we may see those images in the second Odyssey pass that occurs late at night. Then basically the way the Mars and the orbiters work is that the spacecraft or the rover is sitting on the surface, and the orbiters continue to go around, but they're not lined up with where the vehicle is. And so we have to wait 12 hours essentially for Mars to rotate under the vehicle, under the orbiters, and then we'll get our next opportunity to communicate. And because we have two orbiters, we get two almost at exactly the same time the next morning here on Earth, 11:30 in the morning, 11:40 in the morning for Odyssey and for MRO. And so again, that would be the next time where we would hope to hear from the vehicle. And again, depending on what has happened during EDL, as well as what happened in those first few minutes after landing, this could be, in fact, the first time we hear from it, depending on what has occurred. So those are the overflights from the orbiters. In addition, we have the ability with the rover using its high gain antenna, you see here, to communicate, and its low gain antenna to communicate, which is right here, to communicate with the Earth directly to the Deep Space Network. And so because that's a very much farther distance, the vehicle's transmitter is not that strong, we don't actually expect to get data from that communication path, but what we do is what we call a beep, which is a little bit like a tone during EDL, where the vehicle essentially just transmits a signal and through the low gain antenna, and it tells us that it's there and that it's running the sequence that we expected it to see. And so that will be the first time that we get a direct communication without going through the orbiters. And it'll occur, depending on what path we're on, somewhere in the 5 to 6 p.m. The following night, next Monday night. So that would be our first direct path. Assuming that we do hear from the vehicle, we then transition into what I would call normal surface operations. And the big difference between normal surface operations and what we're doing now, again, is really the uncertainty. There's just lots of things that are different about this vehicle on the surface. It has different power configuration. It has the environment that it's in we don't know anything about. So there is a lot of uncertainty into how quickly we'll be able to do things. But if we go to the next chart, I wanted to give you some idea of kind of what the plan is. And you'll hear lots more about all this each day as we go along from Mike Watkins and Jennifer Trosper, the mission managers, as to what the plan is each day. But I kind of wanted to give you the big picture view of what we're going to try to accomplish as we get through the first few days. So the first day, as I said, after we land, is really just to get the vehicle stable on the surface. And it's also then to get prepared to deploy the high gain antenna. We do communicate with the high gain antenna, but it requires knowing where the vehicle is in order to point the high gain very precisely at the Earth. And so the first thing we need to do is to deploy it, and then to figure out essentially where to point it so that we can communicate directly to the Earth, and as well as send commands through the high gain antenna. The next day, we would then deploy the mast, the RSM, and that will give us the ability to take pictures with some of the cameras that aren't accessible otherwise. So that's why, for example, our first pictures are the HazCams, but after a couple of days, we should be able to take NavCam images and begin to do mastcam images as well. On the third day, we will do a checkout of all the instruments just to make sure that they're all still functioning, sort of a very simple aliveness test for the instruments. And as I mentioned, will be our first chance to take a panorama we'll have gotten these little postcards of the area in front of the rover, but this will give us a chance to get our first 360 panorama. Then on the fourth day, we basically have a quiet day. The panorama is a big set of pictures, takes up a lot of data volume, and so we want to essentially not do a lot else other than just send that data down and have it on the ground so that we can begin to plan what to do long term with the mission. Once we get past that, then we transition to an important engineering activity that will take several more days, which is that we have a set of flight software which we've used during cruise and the landing event, but it doesn't have all of the functionality that we want to use for the surface. And so we want to transition flight software versions, basically. The flight software version that we're transitioning to is already on the spacecraft. It's already been loaded up there, but it's not running. It's not active. And so it will take us several days, actually, to transition over to it and begin to use it. If we go to the next chart then. This I kind of talked about already, but just to talk a little more about the products we expect to see as we go through this. And there have been various press releases already talking about this at some level, but just to reiterate, the main idea for the first night is to get these black and white low resolution HazCam images. And again, we expect to get thumbnails, which are very low resolution, like the 50-bit or 50 pixel by 50 pixel kind of little thumbnail postcards. And then we hope to get that first night a more like 512 by 512 pixel kind of image, again, black and white, looking out the rear of the rover. After we get through that first day, then we'll start to send down the MARDI images that Mike Malin talked about a couple days ago. That's the descent imager. We'll start sending down the thumbnails of that. So selected images as we were going down through the landing event, we'll take those pictures and send them down. The first color picture, we're actually using the MOLLE camera that's on the end of the mast. And we're actually sort of looking out sideways out the rover, and we'll take our first color image using it and send it down on the third day or so. And then, as I mentioned, we'll eventually get to doing the NavCam panorama, and that will take several more days to get, that's when it will start coming down on the 9th, and it will take several more days to come down. And again, this is the nominal plan. Clearly, if the vehicle is experiencing issues, or if we have other, we're trying to work through, problems, that we'll have to change this plan in response to that. Once we get beyond the first few days, then I just laid out a little bit of what's the long-term plan for the first couple of months, first 2 or 3 months. And again, I think Pete probably mentioned it the other day when he was talking, Pete Tysinger, but this is a very complicated vehicle. It's way more complicated than MER or other vehicles we've flown in the past, and so it's going to take us a while to first check it out and then to get into the science that John Gratzinger and Ashwin and everybody else wants to do. This is sort of our nominal plan. Again, it's going to be responsive to what we find. We're going to spend almost the entire month of August really checking out the vehicle, getting the first images. We will obviously be getting science data during that, but we'll also be doing engineering checkouts of the instruments, of the sampling system, changing flight software, doing other things. Hopefully by early September, we'll be at the point where we can do our first drive and have the vehicle begin to move around a little bit. And then beyond that, we'll go into the sampling where we first do a scoop sample in late September probably, and then a drill sample sometime after that. October, November is what we're expecting at this point. So I think that's my last thing on the planned activities. Let's just go to the next chart for a second. Quickly, but to finish up, one thing that people are always confused about, and so this is our effort to try to explain it a little bit, is the difference between Mars time and Earth time. I tried to give you calendar days on the previous chart to sort of tell you when we expect to get things, but obviously in reality, the rover and all of the operations team, all 700 people if you count the scientists, are all working on Mars time, where the vehicle, to be synced up with what the vehicle is doing. A Mars day is about 40 minutes, 37 minutes longer than an Earth day, and so in fact, the relative clocks or days shift over time. We land on Sol 0. And it more or less corresponds, as I said, to about 3 o'clock when we land is like 3 p.m. on Mars, and then that every day basically the relative correspondence between the Earth day and the Mars day will shift by 40 minutes. And so you can see we'll be Sol 1, August the 6th primarily, Sol 2, August the 7th. Eventually they'll drift to the point where we will instead of having to have people here in the middle of the night to watch the rover, it'll be during the day, and that will be okay for a couple of weeks, and then it will shift back again. And so you can imagine that it's like losing a time zone every day. It gets pretty tiring. But it'll be exciting because we'll be operating this vehicle on the surface, and so I think that will get us all inspired to work on Mars time for at least 90 days is the current plan. So with that, I think I've spent my time, and I will turn it over to Ashwin to tell you about the weather.
All right. We always make you wait to the end for the weather report, just like if you remember from a couple days ago, I'll just go over why we care about the weather on Mars. There's two things that determine the accuracy at which we land. Basically, the size of that ellipse that we were placing in that flat area next to Gale Crater. One of them is how accurately we enter the Mars atmosphere at the top of the atmosphere. And as you heard from Arthur, we're coming in really nicely down the middle. So now, the next thing that could affect the accuracy of the landing is how well we've been able to predict the conditions at Mars in the past few years based on data from previous missions that we then use to simulate the EDL, the entry, descent, and landing into the atmosphere. We continue to monitor that. We've designed the spacecraft to basically handle all the conditions that we've seen in past years, whether they're clear or dusty, but we continue to monitor it in real time, getting data from the orbiters at Mars every day this week to make sure we understand what conditions the spacecraft will encounter as it's flying through the atmosphere and just how accurately we can expect to land. So I left you 2 days ago with a bit of a cliffhanger. We had seen a local dust storm south of Gale Crater. This had the possibility of evolving in a few different ways. One thing, it could have drifted towards the landing site. That would have been kind of the worst case. It would not have impacted our ability to land safely, just maybe that caused us to land less accurately than we would like, a little further out towards the edges of that ellipse than the center. It also could have disappeared. That was actually the prediction by our atmospheric scientists on our team, that it would disappear within a day or two after seeing it 2 days ago, or it could have just drifted along the south polar cap where these storms tend to form. So let's see what happened. The Mars Reconnaissance Orbiter has taken global maps of Mars for us using the Mars Color Imager, and my colleague Bruce Cantor at Mail and Space Science delivers those maps to us every morning at 7:30 or so. And I'll show you on this Earth map first, just to orient you of how we view Mars in the same map format. Again, I'll point out north of Australia there, just about Indonesia, there's a little circle drawn on the map, and that's where Gale Crater is in the same location on Mars. So now if you go to the next Mars map, this is the most current map of Mars taken 2 days ago on August 2nd. What has happened is the good scenario, where that active dust storm, which was boiling at the surface and very well defined 2 days ago, has now evolved into a fairly harmless cloud of dust, basically the poof remnants of what was that dust storm. And that dust cloud is translating. It probably will not reach Gale Crater by the time we land, and if it did, the amount of dust in that cloud is not believed to affect the entry, descent, and landing in any meaningful way. We continue to see the water ice clouds over Mars. This is a good thing. We've predicted in years without bothersome dust storms, there should be a lot of water ice clouds in the atmosphere because a cold atmosphere that's free of dust tends to have these water ice clouds at this time of year. So the more we see these clouds, the more we like it. Mars appears to be cooperating very nicely with us, and we expect good weather for landing Sunday night. We're going to continue to look at this one more time. Tomorrow morning, we'll get some more recent data. And then I'll show you one final thing, just to show you what could have happened. We have 3 prior years of Mars data from the Mars Reconnaissance Orbiter. And what this image shows is a map taken by the Mars Color Imager 2 Mars years ago. This is from October 2008. Just at the same time we'd be landing the spacecraft on Sunday night, but 2 full Mars years ago. And you can see that there's remarkably few water ice clouds. This particular year, Mars transitioned from its colder southern winter to its more dusty southern spring and summer earlier than we would have arrived if we had landed 2 years ago. And the atmosphere warmed up, the water ice clouds disappeared, and the conditions in this year were very ripe for a lot more dust activity. In fact, days before and after this particular image, there was a lot more dust storms. And that's actually what we took into account when we designed the entry, descent, and landing capabilities for this mission. We had to be able to land in all the conditions we'd seen in previous years, and so that's what we've done. But fortunately, Mars is playing nice, and we're going to get good conditions for Sunday. I'll turn over back to you, Veronica.
All right, thank you. We're going to open it up to questions here in the auditorium. We'll start with the news media, and then we also have our NASA social participants here today with us, and we'll take some questions from them as well. So if you would raise your hand, and we'll get the microphones to you, and please give us your name and affiliation. We'll start here first, and then we'll go to the aisle next.
Thank you. Olivier Sanguy, enjoyspace.com from France. I'd like to know, in the first data you will receive from Curiosity, will you have a sort of health check of the rover, or just a beep?
So it depends on when we hear from it. That under the best case scenario, where we see the data from in each Odyssey pass, those 2 Odyssey passes that'll be Sunday night and early Monday morning, in both cases we'll get health data from the rover that tell us how it's doing. We could have to wait until the next morning though, depending on what happened, and both on our side as well as Odyssey. Odyssey, clearly if it has something happen that causes it to not be listening, then we wouldn't be able to get that data down. So it's very much a question of what happens as in real time as we go through the evening.
Okay.
Emily Lakdawala from the Planetary Society. I know that Mars Express is going to be recording a signal. There's been conflicting information about whether there's actually going to be any data contained in that signal. And so I'm wondering if you can tell me about that and of what use that data might be, considering that Odyssey and Mars Reconnaissance Orbiter are going to be so much closer and receive better information.
Sure. The Mars Express spacecraft will be recording essentially information about the UHF signal. It's kind of like if it's there or not, and we'll be able to see the carrier signal either be present or not in the Mars Express data. And so you are right, we are not going to get actual digital data from that from the Mars Express spacecraft. We'll get a spectrograph, if you will, of what the radio heard during entry, descent, and landing.
It also doesn't occur in real time either. We get it, it's like MRO, where we'll get it recorded. They will record it, and then they'll send it to us a couple hours after landing. So.
Okay, we're going here next, followed by Leo over here, and then on the other side.
Hi, it's Craig Cavalt with America Space and Aerospace America. Question about the DSN configuration. Which DSN station will be the prime one on the landing night when you do go over the hill, and discuss DSN antennas further as to which ones are going to be the workhorse?
So our Canberra DSN stations will be prime for EDL. We also have antennas at Parkes and at New Norcia in Australia, which will be tracking the spacecraft.
Leo Enright with Irish Television. I think probably for Steve Sell, although Richard Cook is pretty good at reassuring us over the years. I was looking at things that might go wrong last night, and so I thought I found something that I hadn't noticed before. And that's a thing called the parachute sabot. There was a description somewhere that I read last night which described this thing deploying the parachute and then recontacting with the descent stage to the point that it was quite violent and might even damage one of the radio antennae. Was I being over alarmist?
You might be mixing a few things there. We do have a parachute closeout lid, which is essentially the top of the I guess you can see it right here, the top of the thing that closes out the top of the parachute cone. That does get pushed off the top of the spacecraft when the parachute deploys, but we've done lots of analysis on exactly how that lid behaves after deployment, and it should drift off to the side. We don't expect any recontact there. I'm not sure if that's what you're referring to or not.
Morning, Irene Klotz with Reuters. I have two questions. The first is for you, Doug. You all have done a really good job in words and pictures of describing the risk of the entry, descent, and landing, but NASA is an agency of numbers, and I was wondering if you did have a probabilistic risk assessment of landing successfully overall, and if there was any particular element in the descent that, from a numerical standpoint, from a risk assessment standpoint, is riskier than the other.
I don't think there's a single number that we can put on this. We rate this. Everybody gets to feed into the risk decision process and the risk understanding process, and so we've collectively agreed that this is as low a risk proposition as possible. But it's almost impossible to put a single number on the probability of success from the top of the atmosphere to the bottom. So, Irene, there's not really a single number. There are analyses that are done, and so you can relate those to risk in every event that occurs. But I think that, it's just such a complicated environment that I don't think that any single number is useful, to tell you the truth. Richard, do you have a different view of that?
No, I think we do, and Steve could certainly talk about it a lot more. We do simulations, Monte Carlo simulations, thousands of cases where we simulate all the different parts of particularly the flight trajectory, the flight dynamics, how the vehicle will, use guided entry algorithms and all that, and we get numbers from that. But that only represents some parts of what the potential risk areas are. It doesn't include things like will the hardware do what it's supposed to do? It assumes that all the hardware will do what it's supposed to do, but it's not, and you get a number that comes out of that, but it doesn't then roll in what's the probability that you might have a problem with the parachute or whatever. And so it's hard to point out a single thing where it all comes together in one, as Doug said, in one integrated number.
Okay, thanks. And for Arthur, could you please explain a little bit more about what that last planned data relay to MSL tomorrow night with the backup computer, exactly what that does? And for Steve, if you could give us the altitudes of the MRO and Mars Express at the time of landing. Thanks.
Yeah, actually, that activity is not a relay. It's a commanded activity on the spacecraft. It's our plan. It's been our baseline plan to activate our backup computer with a set of software that, if in the event, very unlikely, the prime computer reset during EDL, the backup computer would take over and land the spacecraft. So it's always been in the plan to do it at this time, and it's our last remaining, significant operational activity.
And as for the altitudes of MRO and Odyssey, I'd have to get back to you on that. I don't have the exact numbers of those.
Okay, we're going to take a couple questions from this side of the room, and then we're going back over there. Go ahead.
Todd Halverson, Florida Today and USA Today. I was wondering who is responsible for bringing the peanuts into the Mission Control Center. And I was also wondering if one of you guys could give us an idea of what your day is going to be like tomorrow, if you have any landing day traditions or special activities that happen, during the course of the day leading up to coming into work. Thanks.
Well, on the peanuts, I think it's everybody's responsibility to bring peanuts on
Because
these
of that, we
events.
have 50 jars.
So we have plenty of peanuts.
Plenty of peanuts.
And the mission manager usually assures that we don't run out. With respect to, I don't know, traditions on landing day, I think, it's traditional to take a deep breath when we finally get there and reflect a little bit on how far we've come and where we are. So I think there's a moment of joy and a moment of reflection as well.
Yeah, my version of that would be as well that usually when you get to the last day, there's not that much to do, right, other than to wait. And so usually you get a chance to go have coffee with some people on the team and to do exactly what Arthur said, right, which is to say, okay, it's been a long trip here to get here, and it's going to be an interesting next few hours. And time seems to have a weird sort of rhythm in that last day, right, where it goes real slow for a long time, and then in the last 15 minutes it goes like that, and it really goes quickly, and all of a sudden it's upon us. And so that's what will happen.
Hi, Mark Kaufman with the Washington Post and National Geographic. Editors, of course, are very eager to know when might we know that the thing has safely landed. And I know that there's the 14-minute distance gap, but what should we be telling our editors in terms of the earliest moment, the likely moment, and then I have a second question as well.
I can tell you that touchdowns at 10:31, 10:32, there is some variation on that due to atmospheric changes that change how long we might be on the parachute. But essentially, we're within plus or minus a minute or so of 10:31. And if we have Odyssey coverage throughout, if the Odyssey coverage remains all the way through, we'll be able to follow it through touchdown at that time. As Richard mentioned before, there are scenarios in which we, for any reason, might not have the Odyssey data available, in which case then Richard went through the several opportunities after that we could know what happened.
A scenario that then would be 10:45 or so, and how would we be informed?
No, the 10:31 number is Earth receive time.
Oh,
so,
that's Earth received.
Yeah,
Okay.
so it will. Yeah, that's an interesting thing to point out is that we're actually watching the whole thing on a 14-minute light delay. So it actually touched down 14 minutes ahead of that, but when we find out here is 10:31.
And how would we be informed?
You'll probably be able to tell by us celebrating.
Yeah. When everybody starts high-fiving each other, that's
usually
when
a good
you'll
sign.
know.
Okay.
Under the case that we don't know, then what we're going to go into is we'll have either a press conference or a report out of the MSA, as to what we think we know, and some member of the team, probably Pete, will give a briefing as to what we think we know, and then we'll wait until that next Odyssey pass at 12:30, and we'll by that point, I, by the way, have shifted to a different mission support area, so a different control room. It'll be in a different area here at JPL, but it's and the surface team will be there to sort of monitor whether or not we get a communication signal. But so that would be the next time we would hear from it is at that 12:30.
Okay, and if you would, just one other question. You had said that the entry seems to be picture perfect. Could you give us just a little bit of comparison with other Mars entries? Does this one seem to be more precise, about as precise as others? Have there been others that were way off and then suddenly were able to be brought back in?
I think this is about as good as there is. I haven't seen one better than this one, huh, Richard?
No, I think it's exactly what you said. This spacecraft design, the way that this vehicle is designed to fly during cruise, is the same way as MER and Pathfinder before it, and because of that, they're very, very good as far as navigation. That we have a very good idea of where they are, and so on all of those spacecraft, they did about the same as far as their ability to get it to the right spot. In this case, we have the challenge of not only getting it to the right spot, but also telling it where it is, which actually makes it even more of a challenge. And so that part of it, they're actually doing even better than what we've done in the past. So.
All right, we're going on the aisle here. Go ahead.
Hi, I'm Alan Boyle with NBC News. And I wondered if you could talk a little bit about the scenario where there are no signals received and how long that search is going to continue. I think with the polar lander experience that went on for a while. And then a happier thought would be having plans for MRO to take a picture of the landing site. Are there any plans to do that at a particular time?
Yeah, I guess I should talk about MPL since I remember it better than most. I think that the way we sort of look at it is that there are certainly very credible scenarios by which those Odyssey and MRO passes, in the first 18 hours might or might not happen, and so because of that, we definitely think that we can identify ways in which we would have to wait until the next morning, for example, to hear the MRO pass. The X-band, same thing, that if we, for example, had a problem with the radio, the UHF radio on the rover, it's not going to, we actually have two of them, but it's actually not going to switch over to the backup one on its own, that it would take, for several days, it would take a while to change over to the other radio. So because if, for example, we had a failure of the radio, we would certainly not hear anything from any of the orbiters. So because of that, there's a scenario in which you might say, well, we have to wait all the way until 5:30 the next night to hear from the separate system that does direct-to-Earth communications. And so those are all very credible, or certainly credible situations where we'd have to wait through that. Once we get past that first beep, from the X-band system, if we haven't heard from it in any of those communication paths, including that one, then I think that we would be definitely in the not as, in the more likely than not that we had a problem. And so it would take 24 hours, order of 24 hours to come to that conclusion. There are certainly scenarios that we can come up with, and we've got a lot of smart engineers who can think of, off-nominal paths that can get us to it taking longer than that. But frankly, I don't think they're very likely. And so I think once we get past that first day, we're definitely in the low probability category. So yeah, you asked, are we going to try to take a picture? When will we get it back? They are going to try to send it back pretty quickly after landing, and so we hope that we will get it by the time the next morning comes around. We'll have that picture, but it depends on if they got it and how long it will take them to process it. But we're pushing to try to get it that next morning.
That would be a picture of the landing site post-landing?
No, that's a picture as it's going down.
Right. Is there any
then there is a plan to actually take another picture from MRO of the vehicle, the rover on the surface, the next day. So like 24 hours later, there'll be an attempt to take that picture. So.
Okay, we're going to come to the very front of the room here.
Thanks. Jonathan Amos, BBC News. Just remembering back to Phoenix, I think there was one person in the control room who was tasked with calling out the milestones. Will we have something similar this time so that we know we can follow it?
Yes, we will. Maybe Steve, you can talk to the
Yeah, we will have someone in the control room. Alan Chen is his name, and he'll be narrating the sequence as we go through it. He'll be calling out the tones that we'll be receiving from the spacecraft, as well as the UHF data. So he'll be the voice of mission control that you'll hear in the feed. Alan Chen. Chen, yes.
Let's see here. Let me see where the mics are. Okay, let's go here, and then we'll go back on the aisles.
Jackie Goddard for the Times of London. First, Steve Sell. I apologise if I haven't grasped this, but I just want to be clear. This all-important beep that tells us that it's down and landed, what form does that take? What do you see? Do you see a line of code? I think you said you don't actually hear a ping, and it's not presumably just saying, I'm here. What do you actually see that we're wanting to...
You asked a very technical question, but basically it's a line of code. We call them EVRs. That basically it's just almost, you can almost think of it as a text message kind of thing. They're very short, and they have a little bit of information. So the touchdown EVR will contain everything from a couple of numbers that tell us how fast it touched down to where it actually thinks it touched down, and so we'll get that information, and it'll appear on our screens. It'll also you'll see that indication on the on the displays that are available as part of the feed.
Do you happen to know what EDR stands for?
Oh, event record.
What?
Event record. Sorry, you can't take the engineer out of the the acronym out of the engineer. Yeah, right.
EVR.
Yeah, EV event R record. Yeah.
Okay, next.
Steve, can I just follow up with Scott Gold with the Los Angeles Times? So it's essentially an either-or situation as far as when you'll receive confirmation that you're on the ground. In other words, if you have Odyssey coverage the first time, you'll receive that at roughly 10:31, and we'll see you high-fiving each other, and we'll know at that point something. If you don't have Odyssey coverage, then it's an either-or scenario, and you won't know anything for sure for another 2 hours, one way or the other. Is that?
Yeah, that if we don't have Odyssey for whatever reason at touchdown, then yes, it would be several hours till we could know anything additional.
Okay. And what might we be, continuing the effort to please our editors on a very tight deadline, what, what might we listen for from Alan Chen to when he offers confirmation to you that something good has been received at 10:31? What should, since we aren't in the room, what should we listen for that would give us an indication that things are progressing as expected?
They will be playing the audio. Alan's audio will be played over, whatever feeds that you happen to be watching. So you'll hear it the same time we hear it, and he'll say that the rover's been, or that we've received the signal that the rover has touched down on the surface.
Thank you.
Okay, let me go. I'm trying to get people who haven't had an opportunity yet. So we have one in the back there.
Hi,
And
Steve
then-
Gorman with Reuters. My editors are also interested in they want to know when this thing hits the atmosphere at 13,000 miles an hour, I think you're going to be getting a beep that alerts you that that's happened. Is that right?
Yeah, that's right. The tones, kind of some major events that we'll get by tone only. We'll get cruise stage separation. Let me give you some Earth receive times on these. So around 10:14 or so, 10:14, you'll receive cruise stage separation tone for that. We should get an entry tone at around 10:24, about 10 minutes later. And then, like I said, there are a couple more along the way that we use to tell how far along the spacecraft has gotten during entry, descent, and landing. So we send out some tones when we start the turns, the bank reversals, and when we are deploying the parachute and things like that. But we, like I said in my at the beginning, the Earth will set from view of the spacecraft at some point while we're on the parachute. So at some point, about a minute or so after the parachute deployed, we will no longer be able to receive those tones, and we'll be relying on the data relay through Odyssey for the remainder of landing.
Okay, and can I just so if for some reason there's not a tone when the thing, you don't get the Odyssey is not available when the thing actually lands, and so you don't know whether it's landed or not. I believe you guys said the next opportunity for you to get some data would be at 5:30 when there's an MRO overpass, 5:30 a.m. our time?
No, it's so, yeah, so let's go through it again here. It's a little confusing because Odyssey is there and it's sending us data back in the bent pipe mode where he was saying you get the data essentially in real time. In addition to that, though, MRO is flying over at the same time and it's recording all the data.
Okay.
And so during the middle of the night, that data, after the Odyssey pass, actually, that data will get transmitted back to the Earth, and we will start processing it here on the ground to see whether or not MRO recorded the
Anything that Odyssey missed,
or if Odyssey missed the whole thing, MRO certainly could have been recording it. We just won't know until that data comes here to the ground and we process it and we go through and do the signal processing we need to do.
And how long will it take before you receive the MRO, the pre-recorded, if you will?
I think it gets to the ground in about an hour and a half after landing, and then it will take us somewhere between an hour to an hour to determine if there was a signal there, and then about 4 hours to get the telemetry data out of it that tells us what the spacecraft was doing during
But
the
Odyssey wouldn't have another crack at it for another 12 hours or something.
Right, so it's sort of, there's an interleave set of things. Odyssey is doing its own thing. Odyssey has the pass that's at 10:30, and then another one at 12:30 at night, right? And so we
12:30
could-
a.m.?
12:30 a.m.
2 hours after the
After landing. That's right.
So is it possible that Odyssey might pick up something on its second pass at
It might,
12:30 that
absolutely.
you still wouldn't have found out about because MRO still hasn't transmitted it back to you?
That's right, exactly. So there's various scenarios by which we might find out either from an Odyssey overflight that occurs 2 hours later, or when we go back and process the MRO data, or even when we look at the Mars Express data, which kind of shows up in that time frame as well. So all throughout that night, we're getting various pieces of information, and in all of these cases, each of the spacecraft is retransmitting it a couple times, because we could also lose the data, as it's transmitting it. I mean, the orbiters sometimes have data dropouts where the data doesn't all come down, and so they're going to send it multiple times just to make sure we got all the information here on the Earth. Right. The next time the rover will try to communicate to us after that 12:30 opportunity is the next morning at like 11:30 a.m. here, where it will again try to communicate through MRO and Odyssey in a new time that it will try to communicate.
Through the bent pipe, or is that direct?
In the case of Odyssey, yes. In the case of MRO, no. It will record it and send it back.
I mean, the rover you said will next try to communicate directly to Earth?
No, to the orbiters.
To the orbiters, okay.
Yeah, its first time that it will try to communicate directly to the Earth will be at 5:30 on Monday afternoon. So almost 18 hours or whatever after landing.
Thank you.
All right. Well, let me just clarify one thing. Well, we'll be doing commentary during landing, of course, and right after landing, we will switch to the surface mission support area for that 12:30 Odyssey pass. So you will be able to see both that night, the initial one at landing and then the one a couple hours later. And let me see if there's someone else in the room who has not been able to ask a question yet, and then we will invite NASA social participants if you'd like to ask a question. So we'll go right here on the aisle.
Hi, this is Mike Wall from Space.com, and I wanted to ask a question, actually, of the guy who just walked off the stage and coughed Ashwin. This is about Mars weather, dust storms, and such. I mean, you're saying that it's never going to be a serious concern because you've sort of designed this craft to sort of weather whatever dust storm that could be thrown at it. I mean, have you ever seen a dust storm on Mars that is strong enough, big enough, conceivably, to actually imperil the spacecraft, or is it always just kind of an annoyance where it might push it off course a little bit?
Yeah, that's the analysis we did with the past years of data. The guy I mentioned, Bruce Cantor at Mail and Space Science, has spent years counting every dust storm, learning how they behave, figuring out how they evolve over time, how the winds blow associated with those dust storms. And at this season, we realized that if we were to land, right down the middle of a dust storm, we could actually get winds that could, fairly severely affect the ability to time some of the events when some of these critical events happen, because the spacecraft is sensing the conditions in real time. So there could be certain cases where a very violent active dust storm right at Gale could cause a problem, but that's not typical of the season at all. In fact, the risk of an active dust storm right over Gale, we realized was extremely small. It's never actually been seen. Instead, we looked at what actually could happen and the full range of events that could happen, mostly related to dust storms along that south polar cap that push dust towards Gale, and designed the spacecraft to handle the dusty years, the clear years, all those conditions. So this is a very tolerant spacecraft. It's almost putting us out of business in terms of predicting the weather. Previous spacecraft were much more sensitive to the atmospheric conditions, partly also because the spacecraft is so big. The descent stage and rover that flies the spacecraft down are very tolerant to winds at the surface, where previous landers were affected by those surface winds. So we haven't really had to consider winds at the surface much at all. We really just care higher up in the atmosphere, where we're doing the guided entry and where we're timing some of those events like the heat shield coming off and initiating the powered descent.
Okay, here on the aisle, thanks.
Henry Bortman with Astrobiology Magazine. Steve, you described during the descent stage the rocket-controlled back and forth motion of the spacecraft. And correct me if I'm wrong, but that's not only to more accurately position the craft for landing, but it's also kind of like doing switchbacks and controlling or targeting a specific rate of descent?
Sure. So when we first enter the atmosphere, the first thing we do is we enter what we call range control. And if you can demonstrate briefly here, instead of flying sort of straight into the atmosphere where the nose of the spacecraft is kind of pointed straight ahead, we actually fly in with a little bit of a tilt. And that gives us a lift, or we call it a lift vector, which allows us to, as we turn the spacecraft, it will steer it back and forth across, it will steer it in through S-turns. Now, the only reason we do the turns is because if we want to fly higher in the atmosphere where it's less dense, so we slow down slower, we actually turn the lift up. That'll make the spacecraft fly a little bit higher where the air is thinner, and we won't slow down as quickly. And if we need to dip down into the denser atmosphere, we turn the lift to the side, the spacecraft will sink a little bit. And the fact that we have to turn the lift to the side in order to sink the spacecraft causes us to do these turns. And so we don't want to get too far off course. As we start to drift off to one side, we'll flip over and fly the other way. And we just keep sort of flying back and forth. All the while, what we're actually controlling is how high or low we're flying through the atmosphere to stay in a certain range of deceleration to bring us to a stop over the target. I hope.
All right, I'm going to see if there's anyone from the NASA social event that would like to ask a question. We have one here in the front. If we can get a microphone to her, raise your hand a little higher so they can see you. And then give us your name and where you're from.
Hi, I'm Rachel Sanders. I guess I'm from the internet. So you were talking about the landing of this, and so can you talk a little bit about how it tries to land in that ellipse, how it does any hazard avoidance, where it decides to land and things like that? Thank you.
Sure. Basically, we load on board the spacecraft a target, so a latitude, longitude on the planet that we're trying to fly to. And right before entry, descent, and landing starts, you may have heard us talk about entry parameter updates that we do periodically. And all we're doing there is we're telling the spacecraft, when you start entry, descent, and landing, you are here. So you can imagine you're given a map, and we're putting the dot on the map of where the spacecraft is starting. And so on board, it's constantly sensing how much it's turning and how much it's slowing down. And so it's sort of calculating where it is on that map and trying to fly itself to the target that we have preloaded. Now, we don't do any hazard detection and avoidance. We sort of did that manually ourselves by placing the ellipse in an area where the number of rocks or slopes that would exceed the capability of our touchdown system, where there was low probability of encountering stuff like that. So we find a nice safe place to put the ellipse down. So we put it down, we pick the X marks the spot, and we tell the spacecraft fly to that X.
All right, we have time for one more question, and let me see if there's, you have not asked a question yet, correct? Okay, let's take you, and then others, you can come up after the press conference and ask some more questions.
Brad Snoder, Western Washington University Planetarium in Bellingham, Washington. Do you have an idea in mind for naming the rocks in the landing site?
Yeah, it's a good question. I'll start just with some of the bigger features. Gale Crater was named by the people who name these things on planets, the International Astronomical Union and the other mappers. He's an Australian astronomer who lived a long time ago. We didn't come up with that name. Also, that same body has named the major features on Mars for the historical, what they call albedo features, going all the way back to telescopic days. They're bright and dark patches on Mars. And the closest one of those features to Gale Crater is called Aeolus. And so the official names really of the mound inside of Gale Crater where we're going is called Aeolus Mons, Mount Aeolus really in Latin, I guess. The team has also informally named that feature inside of Gale Crater Mount Sharp in honor of Robert Sharp, who was a planetary geologist at Caltech, and really one of the founders of planetary geology, who brought Earth geology to Mars in the early days of the Mars Mariner missions. Once we get on the surface, we'll start naming those smaller features as well. And the team is still working through exactly how that'll happen. What they have done, as John Grotzinger told you a few days ago, is divided the entire area where we're going to be exploring up into these quads, this grid pattern. And each scientist on the team who has been looking at that grid will come up with a naming scheme for features in that area. That's sort of how we'll go about it. I don't have any of those for you right now, but that's something that we'll be working on.
Okay, I'm told we have time for one quick question and answer. So I'm going to go with the hand I saw first, and that was over here on this side, all the way up on the aisle. Thanks.
Irene Klotz with Reuters. Ashwin, could you just describe the other, I guess, the scene at Mars? As you said, it's going to be 3:30 in the afternoon there. What's the temperature? What do you expect the winds to be? What color are those ice clouds? Thanks.
Sure. Yeah, based on our orbital reconnaissance, we believe that there'll be a little water ice haze. So it'll be a late afternoon day on Mars when we land. We won't see this right away with those black and white pictures, which are more pointed to the ground. But in the next few days, we'll be inside this deep topographic hole on Mars. Gale Crater is a hole punched into the surface of Mars. And as such, there may be these water ice clouds that a haze overhead. The sun will set, on the rim of the crater, maybe a little earlier than it does in other places, because we're inside this hole. We'll be looking out towards the mound. The skies will be pink, of course. We are in an equatorial site, so we won't have a big seasonal range of extremes over the year. That's one thing that actually worked out pretty nicely with this site. But it is cold. It's Mars. So we expect temperatures maybe at plus 10 Fahrenheit or so in the day, and maybe minus 100 or so Fahrenheit at night. So it's a good swing of temperatures. And the spacecraft, of course, and all of its instruments had to be designed to withstand all these things. The winds are going to be interesting. In fact, our meteorology team is getting more and more excited about measuring the winds with this rover at this site, because unlike other flat sites we've had to land at before, the topography itself is going to be driving the winds at this site. There's going to be winds coming down from the Gale Mountain. Basically, these are katabatic winds that form because of the topography as air heats up differently. And so this wind will come down the mountain in the afternoon and rise up the mountain at night. Won't be violent, no harm to the spacecraft, but we'll be able to measure really how the winds swirl around inside this crater. The final thing is that you may notice that there's dune fields around the Mount Sharp. And one of the interesting things we'll be doing is trying to understand how that complex wind field inside this crater has resulted in the geologic story at Gale. How has it eroded the mound? And how has it moved these dunes around that we see today?
All right, that's going to conclude today's news conference. Thank you so much for joining us. I'll give you a little bit of the schedule for tomorrow. We will be back at 9:30 a.m. tomorrow Pacific time for our final pre-landing briefing and a new update on the status of the spacecraft and landing. At 3 p.m., we invite you to join us for a chat with NASA Associate Administrator John Grunsfeld and JPL Director Charles Alachi. And our commentary will begin tomorrow evening at 8:30 p.m. Pacific Daylight Time. We hope you will join us for that. Thank you so much for joining us, and broadcasters, please stand by for a replay of today's images. Thank you. Good morning and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Veronica McGregor. We are here for the final pre-landing news conference to discuss the landing of the Mars Science Laboratory Curiosity rover, scheduled for this evening at 10:31 p.m. Pacific Time, 1:31 a.m. Eastern Time, just a little over 13 hours from now. I'm going to introduce our panel to give you the final update on the status of the mission this morning. Joining us today, we have Doug McQuistion from NASA headquarters. He's the Mars Exploration Program Director. Brian Portok of the Jet Propulsion Laboratory. He's the MSL Mission Manager. Tomas Martin Moore from JPL, the Navigation Team Chief. And Adam Stelzner from JPL, the Entry, Descent, and Landing Phase Lead. And we'll begin with Doug McQuistion.
Well, it's a fine Martian day we have. The sun's about ready to come up at Gale Crater. It's going to be warm. It's going to be sunny. Probably get a nice tan if you want to do that. Plenty of UV available. So you'll hear more about the weather, I think, from Adam. MSL is now feeling the effects of Mars, and I think maybe the team is. I know I am feeling those effects as well. We're, to be exact, 12 hours, 59 minutes, 33 seconds from touchdown, and about 112,000 miles to go, accelerating all the way from this point on. We're about to land a rover that is 10 times heavier than Spirit and Opportunity with 15 times the payload. Pretty incredible feat we're about to attempt. So we may not be successful. What the outcome of this is, we'll all know, but one of the things I want to go back for all those inquiring editors out there is the communications information and how will we know and what will we know, when will we know it. So at the very top level, Odyssey is our primary information path. Odyssey is going to roll the spacecraft a few minutes prior to MSL entering the atmosphere. It will, as long as that maneuver is successful, it will watch MSL and Curiosity all the way to the ground and a few seconds after. That will be the equivalent of a bent pipe or real-time information, obviously light time delays considered. If we do not have Odyssey in that configuration successfully rolled, if it goes to safe mode or lockup doesn't occur, whatever, the next Odyssey pass will be around 2 hours later, about 12:30 a.m. Those are our two best opportunities to understand what the status of the rover is on the surface. The other assets will be listening, but we won't know from them for a considerable number of hours later. So that is the key, is Odyssey. So I want to make sure everybody is clear on that. It might be Monday morning before we understand it if Odyssey isn't successful with that. But if we are successful getting to the ground and we're successful with Odyssey information coming back, we are going to have the opportunity for untold discoveries. This location in Gale Crater is absolutely amazing, a place we could never have thought of getting to just a few years ago. It's a 2-year mission, not a 90-day mission, so be patient. We're going to be doing this thing sequentially, intelligently, smartly. It's a complex system. I hate to use the analogy again, but I will. It's a marathon, not a sprint. So we will keep people informed, we'll keep moving forward, and it's going to be exciting. There's years of exploration coming. The other thing that inquiring editors want to understand is imagery. So I'm going to talk to you about, briefly, first images. So if you'd bring the graphic up, please. A little animation here. On the front of the rover here, down low on the deck, is the front hazard cameras. What's important, we'll spin around to the back, the first pictures will be taken just shortly after touchdown by the rear hazard camera, which you see here, with covers on. The covers are transparent. The covers will come off, but that first picture is taken with the covers on. So we don't know what we'll see through that. We don't know how much dust will be on those covers, but what's most important is we don't know if the timing of that picture being taken and Curiosity transmitting it will actually be while Odyssey is still in contact with it. The timing is tight, so we might not get that rear haz cam image. If we don't, Odyssey probably is already gone when the front haz cam will open its cover and take an image. But we won't get that image back. The first chance of getting that back is that Odyssey overflight at 12:30 a.m. Okay, so I'm not sure what the probability of success is on that rear has-cam image, but I'm not going to lay a whole lot on it. So be patient. 12:30 is a much better opportunity to get that first image. So what does that first image look like? If we can bring that graphic up, please. The hazard cameras are designed for the nav team driving on the surface to be able to see where they're going and what the problems are. These first ones are thumbnails. I mean, they're truly thumbnails. And what you see on the bottom left is actually the actual size of the image that we'll get back, pretty small. We've blown it up on the right, so you see that it's even not a very high resolution because it's such a low-res picture. It's going to be kind of fuzzy. What it'll tell us is, yep, there's Martian ground under us, so we are actually on the ground. We got to the planet we wanted to get to, and it'll give us an idea of what we have. The front has cam, and again, it may be a dusty image if this is the rear one. If it's the front one, the covers will be off and it should be clearer. It'll still be kind of pixelated. Higher resolution images will come later. Adam can probably give us more on that. I don't have the exact timeline. But that hopefully helps a little bit on the communications process and what the first images in the first couple of hours on the surface are how that's going to work. In the days, years, weeks to come, there's going to be enormous number of images, incredible images, color images, real color this time too. So kind of like the human eye will see, which will be really exciting. And those will come, and there'll be plenty of those. So tonight's it. Super Bowl of planetary exploration. 1 yard line, one play left. That plays about 12 hours from now. We score and win, or we don't score and we don't win. No matter what happens, I just want the team to know I am really proud and I'm actually privileged to have worked with these guys and gals. They're amazing. We've done everything, they've done everything humanly possible to make this happen. If we don't do it and we're not successful, we'll pick ourselves up, we'll dust off, we'll do it again. The science is on the surface. We need to keep going back, and that's the plan. But I think we're going to stick the landing. Brian, over to you.
Thanks, Doug. So Curiosity has traveled over 566 million kilometers on its way to Mars at this point, and we only have a few kilometers to go to this evening. I'm going to give everyone kind of an idea of the status of the spacecraft and what the flight team has been doing over the past 24 hours and what we're going to be doing leading up to EDL. So the flight team right now is diligently monitoring the spacecraft and the ground systems, and I'm pleased to say that both systems remain very healthy. The spacecraft is in EDL approach mode right now, and it will transition to its next mode, which we call EDL main mode, just before entry. The spacecraft is pointed in the right direction. It's about a degree, the antenna is pointed about a degree off of Earth and about 37 degrees away from the sun. The solar rays are generating ample power, and the battery state of charge is 100%. So we're ready to head in and get the rover going. So we continue to have a strong communications link with the DSN. In cell phone speak, we have a full set of bars, 4 or 5 bars. So that's been going well. And we have a steady thermal and propulsion system at this time. So over the past 24 hours, we've been doing some work on the spacecraft, just getting it ready for EDL. Yesterday morning, we decided to make a small adjustment to a parameter for EDL. This will help improve the accuracy of the data that's generated by inertial measurement unit during EDL. Just after lunch, we went through an EDL milestone, so an autonomous action that is done by the spacecraft, and that was called the MLE anchor. And at that anchor, we basically turn on some heaters that will warm up the cat beds for the landing engines. So those have been on since yesterday, and they're nice and toasty and ready to go. Yesterday evening, the flight team also configured the backup flight computer, so the remote compute element, so that it's prepared for EDL. So there was some software on there that we had to get configured, and now that's ready to go just in case it's needed. This morning, we determined that the final opportunity to adjust the flight path, so what we call TCM6, is not needed. So the flight path is looking good. and we decided to waive off that opportunity. We also decided to not use an opportunity to update the spacecraft knowledge of its flight path. So not only do we have to hit the right point at the top of the atmosphere, but the spacecraft also has to know where it's going. And so we didn't have to take an opportunity to do that. The knowledge we have on board looks great. Okay, so leading up to EDL, we have one more opportunity, if we choose to use it, to update the knowledge of the flight path on the vehicle. We expect that this will not be needed at this time. However, we're ready to use it if we decide to do so. We're going to continue and monitor the autonomous EDL timeline actions. So we have a number of them to go today leading up to EDL, and so the flight team will make sure that those all get executed properly. Then basically we're going to be joining all of you and everyone across the globe, glued to the edge of our seats, just ready to experience the big event. Once we're on the surface, the rover will transition to surface mode, and it'll start to execute its first instructions on the rover. And it'll prepare for the first Odyssey communications pass that Doug spoke to you about. So the flight team is feeling really good at about the spacecraft at this time. They're very excited for the big event, and they're ready for what's to come. Yesterday, Arthur Amador, the other mission manager, was up here talking to you, and he got a question about team traditions that happen before big events. And I think he talked to you all about peanuts and how they give good luck before these kinds of things. So I thought I'd bring up a couple of traditions, more individual traditions that a couple of the folks on the team have. One of our engineers in the uplink area named Matt Lenda, he grew what is his version of what would be a playoff beard. He kind of had these mutton chops that he was growing leading up to EDL. Nagi Cox, who is also another uplink engineer, she basically is going to be holding on to these two trinkets all day, and they kind of relax her. And she's done this for other landing events like MER. So if you see her around, you'll probably see her holding the trinkets, kind of keep her calm during the big event. And we have another person named Babak Ferdowsi. He's a flight director and system engineer for MSL, and he's been working throughout cruise. And so his tradition, and he's had this tradition through all of our system tests and launch and big events during cruise, he basically comes up with a unique hairstyle every time. So he's very well known for this. And before EDL, actually, a few months ago, we actually had a flight team vote about what his hairstyle should be. And the flight team, the majority ruled on the stars and stripes for him today. And so if you see him walking around on the lab, you'll see he's got what you would call more of a mohawk. He's got some red and blue on the top, and he's got some stars on the side. So all those things are, they work to keep people calm, kind of keep the mood light, and also result in some good luck for Curiosity. So the spacecraft is also ready and continues its very accurate flight path towards Mars entry. And the person responsible for that excellent navigation is here to my left, and it's Thomas Martin Murr.
Just to make clear, I'm not the only responsible for this navigation. We have a whole navigation team and support teams like the propulsion team, the ACS team, and the Deep Space Network that are helping us to do this good job. Curiosity is right now about 100,000 miles from Mars, and it's approaching Mars at a speed of about 8,000 miles per hour. As it gets closer to Mars, the gravitational pull of the planet is going to accelerate the spacecraft to a top speed of about 13,000 miles per hour, that then the EDL team will have to take care of. The navigation team is continuing to receive tracking data from the antennas of the Deep Space Network. We will keep using this tracking data to monitor the trajectory of the spacecraft, and so we can, if necessary, update the entry state in the last opportunity. Just a reminder that the last time that we updated the entry state of the spacecraft was on Monday, 6 days ago. We have been able to predict the trajectory of the spacecraft over a distance of, I think it's more than 1 million miles, to an accuracy of something like 500 yards. So that's pretty good. Over the last night, we saw the effect of getting closer to Mars on our tracking data. That is when it's more evident. And it's in the last hours of the trajectory that the prediction errors, either on the trajectory of the spacecraft or the planetary ephemeris on Mars, make themselves evident. But the evidence this morning that we saw is that things are very well predicted. Another team that we need to thank is the team that prepared the planetary ephemeris for us, that tell us where Mars is, and they have done an excellent job too. As Brian mentioned, the mission control team is not going to modify the trajectory of the spacecraft before entry anymore. The last TCM opportunity, trajectory correction maneuver opportunity, has been canceled. As a reminder too, the last time that we modified the position was last Saturday, and we have canceled the last 2 opportunities, so that's very good too. There is a small leftover delivery error, but we are well within the performance of the EDL system, so EDL should be able to take care of that. Graphics, please. Image. So here you can see where we enter the atmosphere of Mars, where the guidance starts a few seconds later, and where we have the chute deploy and touchdown on the Gale crater. The distance that we will go between entry and landing will be about 400 miles, I believe. And you can see there also the ground track of MRO that will overfly Curiosity as it descends into the Gale crater. The estimate that we have right now of the entry point is that it's just about 500 yards away from the entry point that is in the spacecraft. So that's well within the noise. So that's why we decided not to update the entry state in the spacecraft. And it may be possible, as Brian mentioned, that we will not need to update it anymore before we enter Mars atmosphere. So after processing, we have been, the orbit determination team has been very busy the last months, and the navigation team, and especially the last 96 hours, we have processed millions of Doppler data points, hundreds of or tens of thousands of range measurements, and also hundreds of interferometric measurements that the DSN, the Deep Space Network, is doing using 2 antennas from different complexes. That has helped us also a lot. And we are very confident that we will deliver Curiosity to the right entry point in the atmosphere of Mars so it can safely land into the Gale crater. So next, Adam is going to tell us about those last 400 miles into Gale crater.
Thank you, Tomas. As Brian mentioned, Curiosity is, the spacecraft herself is going through her preparations, getting herself ready for EDL. She's warming some of the engines, the rocket engines that we'll use during EDL, up so that they're ready, poised to begin entry, descent, and landing. As Tomas mentioned, the nav team's done an outstanding job of getting us right on target. And so that leaves it to the EDL team. This team, I believe to be a tremendous team, has worked really hard for the better part of a decade. And the fruits of that labor get put to the test tonight. It's a little anxiety-provoking, but I will say that I slept better last night than I have slept in a couple of years, because she's kind of on her own now. And when I look back at the hard work that we've done, I believe that the team has done everything that we can to deserve success tonight. Although, as we all know, we can never guarantee success. Mars is cooperating. The weather's pretty good. If you could give me Ashwin's slides, our deputy project scientist, Ashwin Vasavada, is down for the count a little bit with a cold, and I'm covering for him. If you look over Australia, you'll see a little circle there. This is the map of Earth. Think of it as a map of Mars. Next slide. And Gale crater is a little bit above where Australia would be on Mars if Australia was on Mars. Looking at this map, you'll see some yellow patches and some white cloudy patches. We like the white cloudy patches. Those are ice clouds. They mean the atmosphere is cold and clear, high density. That's what we like. The dusty stuff, the yellow, warms the atmosphere, makes it a little less dense. We don't prefer that. Actually, Curiosity's unusually adept at navigating the differences between those two and the uncertainties in them. That's one of her special attributes. But for tonight, the atmosphere looks perfect. Although it may get a little dusty after we land, we've got great weather for landing. So the team is ready. The spacecraft is ready. And it's to the fates. I would like to take a moment on behalf of my team to thank both the cruise team, the nav team, IPE, ACS, RTO, DSN. There's a whole bunch of acronyms which envelope tremendously talented folks who have worked diligently and very professionally under a lot of stress for the last months to deliver Curiosity to where she is, ready to do her job. And on behalf of the EDL team, we're very, very thankful. And then finally, just on a personal note, some of the EDL team members and myself, we decided to sign up for some of the social media things that you can do, Twitter and Facebook and so forth, to allow us to make contact with the general public. And the outpour of support and encouragement we've received over the past week or so has been tremendous. So we thank you out there for all the support and all the good wishes. We need all of them. We appreciate all of them. We're rationally confident, emotionally terrified, and we're ready for EDL. Thank you.
Okay, with that, we're going to start taking questions here in the room. And let's see, I'm going to start with news media first, and then we're going to try to get some questions in from the participants of the NASA Social. I'm going to start at the back of the room and move up. Go ahead there and give us your name and your affiliation, please.
Leo Enright with Irish Television. I'm curious, what would happen if the ballast didn't deploy? Is that a survivable scenario? And also, just fishing for a quote, if I may, on a separate matter, what amount of control will you have during those 7 minutes of terror as you sit in the control room, compared to, for example, somebody sitting at home watching it on their television?
I'll take the first bit first. There are two pieces of tungsten adding up to about 145 kilograms in all total, not shown here because this is the configuration of the spacecraft after she's removed them. They're called the cruise ballast masses. Each of them are about the size of a laptop, made out of tungsten, which is a metal alloy that's very heavy and dense. They sit right here, sort of where each of my fingernails would be, and prior to entry, we throw them away, little springs, and we toss them off. And that creates the imbalance that we use to develop lift. It's important that we get rid of those, because without the lift, we can't guide ourselves to the pinpoint target inside Gale Crater, and we cannot attain the altitude performance that we would need. We've done simulations where we only get one of them off. We do remarkably well with those. Our odds are better than 50-50 if we get one of them off, but they're still substantially less than what we think they are with both of them off. So they both really need to get off, and we're very confident they will. As far as the amount of control that the team has during entry, descent, and landing, it's identical to the control that anybody watching at home has. We're all along for the ride.
Okay, the next question is here at the front of the room. Go ahead.
I'm Frank Mooring with Aviation Week for Brian. For the second Odyssey pass, could you give us a rundown on what exactly the rover will be sending up and how it will know that the orbiter is going overhead? Thank you.
Right. So for the So the Odyssey pass that occurs at basically landing plus 2 hours, which will be 12:30 a.m. PDT, that's where I believe our best chance is to get the first images, right, from the surface. So Doug talked to everybody about the rear has cams, would be taking an image, and went through that picture. That's actually what I think the best information is that we're going to be getting at that time, to say, yes, we're on the surface, and yes, things went as expected. So there's a couple things. With the Odyssey pass after landing, we expect to get some spacecraft or rover health and safety telemetry through that pass. So if all is well, then we expect to get that telemetry, and if we do, then we'll know some direct information about the rover health. There are other scenarios where maybe that telemetry doesn't come through, but we see a signal. The fact that the rover is sending a signal to Odyssey, that also tells us a tremendous amount of information that the spacecraft can communicate with Odyssey, and we're getting data from it, and we know it's alive on the surface. So I think those are really the key pieces of information.
Okay, next question is in the front row.
I'm Alan Boyle with NBCnews.com. And I wanted to just ask, maybe Brian, if you could recap again. It sounds as if there's no plan for a course correction and no plan to update the navigation information.
Yeah, so let me clarify a little bit. You're correct on course corrections. We decided this morning to not take advantage of our last opportunity to do a course correction. That course correction was never really expected to be used, but was planned at this time just in case it was needed as a contingency. Okay, so things are going very well with the flight path as we discussed, so we actually went more according to our plan and said, yes, we don't need to use that. So things are going well as far as the actual flight path and entry. We have one more opportunity to update the parameters that tell the spacecraft where it is and where it is entering, so we call it the onboard knowledge. We still have that in front of us. So we went through a decision process earlier this morning to decide whether to use an earlier opportunity to update that knowledge information. We decided not to use that one because, again, the knowledge on board is very good, as Tomas mentioned. So we have another opportunity in front of us to go through a decision process. Right now, with the information that we know, it's expected that we won't use that. However, it's put close to EDL for a reason, and that's in case it's needed. So we still have more data to come.
So the way things look currently, you don't expect that there will be any more uploading of information to the spacecraft?
So I think our general expectation with the data we have now is that we won't need to do it. However, we still go through our regular processes and we collect the data, so we have a potential opportunity to do it if we need to.
So it could be totally watching from this point?
Could be, that's right.
Okay, it's going to go right to the second row again, over here, and then we're going to the other side of the room, and I am keeping track of order of hands going up as best I can. Okay, right, it will go to you next. Okay.
Thanks, Veronica. Irene Klotz with Reuters. Is the picture with the rear has cameras the very first thing that MSL is going to do once it's touching wheels down? And could you go through a little bit about what Curiosity is going to be doing, whether or not there's any information from orbiting spacecraft coming back to Earth or not? So in other words, what's sort of its automated program from touchdown until you guys want to be able to send some commands to it? Thanks.
Sure. So once the spacecraft touches down, as I mentioned earlier, and the flyaway is complete, the spacecraft goes through a mode transition. So and that's more of a flight software thing, but basically what it'll do is it'll say, I know that I'm done with EDL, and I'm now going to go into a surface mode. So it goes through a transition, it configures some of the communication systems and things like that. And then we start to execute what is called the Sol Zero sequence. Now, I don't have all the details about what that sequence does right with me now, but it's basically configuring itself well, the main thing is to start communication with the orbiters and to send us down data on its basic health. So.
And how soon after the landing is the picture taken?
Adam, do you know the time on that?
Yes, about
I'm going to repeat the question first because it wasn't on mic, but how soon after landing is the first picture taken?
about within 4 minutes, just a little under 4 minutes of touchdown, those images are ready to go up. And this is why Doug mentioned there's a bit of a race condition as to when the orbiters go out of link and whether those images will get up before that happens.
Okay, go ahead.
Good morning, Scott Gold with the Los Angeles Times. Can you provide a little bit more detail about your conversation over the course of today with Odyssey? In other words, when will you reach out to Odyssey and request that it start the roll? When will you start to get some good information that it is responding and talking back to you? And when, over the course of the day, would you expect to know, to some degree of certainty, whether you'll have that 10:30 solid information or whether it will be a later pass before you start to get good information?
I'll take a crack at it and let Brian fill in the gaps here. So Odyssey started its EDL sequence already. MRO started it on Friday. So they are both not quite on autopilot, but they're both moving forward with a planned sequence of events. So the communications, Odyssey is in communication with ground on a regular basis through the Deep Space Network. And so it's set to go. So that team will roll the spacecraft, I don't know exactly how early, but it's 10 or 15 minutes, I believe, something to that effect, prior to MSL hitting the top of the atmosphere. That's really the key event. As you recall, we lost a reaction wheel on Odyssey about 5 or 6 weeks ago. So we're still learning about how this spacecraft operates on a different momentum configuration than it's had previously for its past 11 years of operation. We think we have it nailed. The team's done a great job figuring it out, but there still is a bit of a risk in the process of rolling the spacecraft in this new configuration. If we successfully roll it in its new into that configuration where it's pointing at MSL, the reason it needs to do this, a little side note, is it's pretty low on the horizon. Okay, so it's looking across the planet to some extent at MSL, whereas MRO, as you've seen in graphics yesterday and today, goes right overhead. Odyssey's low on the horizon, so it's got to point at it to get a good link margin. So if we successfully roll it, I think we're good, and we will start getting data back right away. Once it's there, we're fine. Okay? So if the risk is that new momentum configuration creates an environment that the spacecraft can't control itself and it goes into safe mode, then it'll be the next day, probably anywhere from 2 to 12 hours before we get it back. That's why there's some risk that we won't actually see touchdown itself. Odyssey is the only spacecraft that can actually see the touchdown event. Earth has set, MRO is recording, Mars Express is recording, and so it's the only real-time asset that we have.
And so just one quick follow-up. So you won't know whether the roll has been completely successful really until 10 or 15 minutes before the atmosphere. So you wouldn't know at, say, 7 o'clock tonight, okay, we're not going to have 10:30 confirmation, or we are. You won't know that until immediately.
Until you do the roll, you don't know. Yeah, you got to do it. So it's all prepped. It's been tested in the test beds over and over. We think we understand how things are working right now. All the parameter files have been checked. Everything's been checked and run through the test bed multiple times. So we don't think there's a problem, but we won't know it until we do it.
Thank you.
And I can
Okay.
get you that exact time. I don't know it off the top of my head, but I think it's pretty
Directly,
short.
well, across there, yes, it's that one first, and then it'll move forward to you. Okay. You can go ahead. Okay, sure.
Thank you. Olivier Sanguin, joyspace.com in France. As you know better than me, there is a Carl Sagan Memorial Station on Mars, so maybe it's a bit too early, but have you already think about doing something like that? Even though there is not a fixed platform like Spirit, Opportunity, or Mars Pathfinder, do you have any names, idea, or is it really too soon? Thank you.
No, I'm sorry.
Yeah.
I was writing something down. I'm sorry. Could you repeat that? Or, unless you got it, my mistake.
I can cover it.
Okay.
Within the team, and I think within the program, people have started to think about what we might do with where we land, but no decision that I'm aware of has been made yet.
Is it formal or informal, an informal process?
Right now, it's informal.
Thanks very much. Ivan Semenik from Nature. Actually, I have a question for Adam. It's about the dust. I just would like a little bit more information about that. The way you described it, it sounded as though the air over the landing site will get a bit dustier after the landing. Is that because there's a weather pattern approaching, how do we
That's
know
fine.
that?
So we're landing right now in a transitional season. I'll play Ashwin Vasavada for a moment here. In a transitional season between the cold and clear season on Mars and the warm and dusty season on Mars. And during that transition period, you get a lot of storms that occur on the pole at the cap edge. They're called cap edge storms. They occur at the transition between the CO2 frost region and the non-frosty region, and that albedo difference generates a lot of vorticity and storm generation. We've been seeing that happening, small cap edge dust storms taking place, and actually in today's data there is a decent sized, again still local, cap edge dust storm just east in the Hellas Basin, and that storm will lift some dust that may become diffuse and may be drawn over the landing site, but the speeds at which the dust could make it to the landing site will take it to the landing site later. And it's very likely that it will dissipate and will be unnoticeable at the landing site. But we have been monitoring on a daily basis for a couple weeks now the weather and tracking things just like this storm. And if this storm had happened 3 days ago, we might be sweating a little bit because we might be worried that it might have come on up to gale, and then we may have chosen to model the atmosphere differently.
So what's the impact on the spacecraft if the atmosphere were a little bit warmer because of the dust?
Once she's on the surface, there actually, even within EDL, there's not really much impact. Maybe some of her margins would have been reduced during entry, descent, and landing, specifically the guided entry portion. She might have had to use some of the control authority that she could have, if Tomas hadn't put us right down the pipe, we may have needed some of the atmospheric, the control authority we would have used for atmospheric variation to handle a delivery error. The delivery errors aren't there, and the atmosphere is right down the middle, so she's in fine shape. Once she's on the surface, dust doesn't really matter to her.
Okay, we're going a few rows back there. Thank you.
Thanks. Hi, it's Bill Harwood, CBS News. One quick one for Brian and one for Doug. For Brian, pictures aside, assuming we don't get a picture on that first pass, what is the actual data you see that shows weight on wheels? I mean, what is it that you would see on a screen in the control room that says this thing's on the surface?
Actually, I don't know, Adam, you want to talk about the EDL com?
We are taking data to confirm that we've touched down safely, and we have 3 different signals that we use to confirm touchdown, and we need all 3 of those things to look right before we say go. One of those is a message from the spacecraft that says I touched down, and this is the velocity, speed I touched down at, and where I think I am. The other is the rover has an inertial measurement unit, a gyro and an accelerometer set, and we look at that stream to say that the rover's not moving at all. So it's that signal says I think I'm on the ground and I'm not moving. And then the third is we wait a safe period of time and confirm we're getting continuous UHF transmission. And frankly, that's there to make sure that the descent stage hasn't fallen back down on top of the rover. And when all 3 of those signals are positive, we declare touchdown confirmation. And then that's, to the best of our knowledge, all that we could see means that that spacecraft, Curiosity, is sitting on the surface.
Thanks. And a quick one for Doug. You mentioned our editors and what folks want to know during landing, and you've also mentioned, that, like any good manager would, that you don't know that this is going to succeed or not. What are the stakes for this mission, success versus failure, in the context of the budget pressure NASA is under in the planetary program and everything else? I mean, I had one guy tell me, oh, if this thing fails, this is just this huge disaster for Mars, and we lose the decade. And obviously, if it succeeds, it's the greatest mission that you guys will have ever attempted. How do you view those two things in the context of what's going on right now with NASA? Thanks.
Well, I think if we succeed, it will be one of the greatest feats in planetary exploration ever, not to mention just this decade. I think it shows the leadership that the United States has had in the exploration of Mars, and our success rate has been pretty darn good recently, knock on wood, obviously. If it fails, I think we need to understand how it failed. But I think that these things are really hard to do, which is why we keep talking about it. Does it mean the end of the program? No. It means that we've had a setback. It means we will step back a notch. We will learn what happened. We will already have some data that we've learned, whether it's the radiation data we've received for the last 8 months of cruise, or just the fact that we understand how to build a system now that can do guided entry and get us into smaller and smaller landing areas. So we've learned a lot from this mission. We will learn from the failure. We'll figure out what the problem was, and we'll go back and we'll do it again. So a failure is a setback. It's not a disaster. And we can learn from it, and we'll move forward.
Okay, we're going to move a few rows forward. There you go.
Henry Bortman, Astrobiology Magazine. I'm still slightly confused about what messages come when. Sorry, I know you tried. This velocity and position message, short message that was referred to yesterday as a beep, that's relayed by Odyssey or that's direct?
I'm not sure what was referred to as a beep yesterday, so I don't know totally how to cover that. There's, upon touchdown, through Odyssey, there is a UHF data message from the rover that says, I think I landed at this speed at this location. And that goes through Odyssey.
Okay, thanks.
Okay, up here in the very front. There we go.
Thank you. I just want to come back to the question of how soon you may know whether you're going to know that you're going to that the thing is gone, is on the ground in real time. So you say that Odyssey, you're going to have to roll this thing about 10 to 15 minutes before MSL entry time. So that's like shortly after 10 o'clock, I guess. Something, you know,
Somewhere around there. Yeah, I'm going to get the exact time.
And then you'll know, will you know right away, pretty much when that roll is supposed to occur, whether it occurred correctly, whether you got the configuration you're looking for?
They'll be in contact with it when we do the roll.
So we can infer from that within, I don't know, like 15, 20 minutes of the scheduled landing time, you'll know whether you should be getting the UHF signal back through Odyssey that would be able to confirm that the thing has landed safely.
Right, so Odyssey will communicate with MSL through its descent profile. So it will be in contact, and that's how we will understand what's happening through the sequence with great detail, as opposed to just tones that was discussed yesterday. And so it will see it all the way to touchdown. Unlike the other assets, it will see it all the way to touchdown, and it will transmit that data back to us in real time as it sees it. Now, that's ignoring the light delay, of course.
Right, but you'll know if it's not available before EDL is complete.
Oh, yeah. We'll know right away. If that roll is not successful and it goes to safe mode, we'll know it right when it happens. Yeah.
Okay, thanks.
Yeah. Next question is further back. Go ahead.
Todd Halverson of Florida Today and USA Today for Doug. In the event of a really, really bad day, there will probably be questions almost immediately about the fate of the RTG on board. And I'm wondering if you could cover the credible scenarios for the fate of the RTG in a crash landing and the fate of the P-238 fuel on board. Thanks.
Sure, Todd. The RTG was designed to withstand launch failure in many different explosive environments, and considering the energetics involved in launch and the altitudes that can be involved, if we crash it on the surface of Mars, it's a much less severe environment than any launch failure. The The plutonium is in what's called clads, and they're like large marshmallow-sized devices, and it's made out of a material that's like a ceramic, so it doesn't powder when it breaks. When it breaks, it's like dropping a plate on the kitchen floor. It breaks into pieces, very discrete pieces. Again, hitting the surface of Mars with it, between what it's designed to withstand and what the surface of Mars is like in comparison, I don't think this will happen, and I don't think they'll break up, because those clads are then buried inside the RTG. But even if it does, they won't disperse into the atmosphere or do any crazy thing like that. They will probably remain intact. We've shot these clads out of cannons at concrete walls, and they don't break. So, the likelihood of any plutonium escape with a crash landing on the surface of Mars is very, very, probably non-credible, but super low.
Okay, let's see. We've got a question here. Go ahead.
You mentioned about if it does all go pear-shaped, that you pick yourselves up, dust yourselves off, and do it all again. There's the small matter of the $2.5 billion you might need in order to do that. To the people who are holding the purse strings and will be influenced in making those decisions in the future, what would you say mankind will lose if we don't do it again?
What will we lose if we don't go again? So let me clarify we'll do it again. We may not do MSL next again, or a rebuild of MSL next. There's many, many very important mobile surface missions that could be done. So we may back up, start a little smaller. We may decide to rebuild MSL, because it is a very important scientific mission. I think we can do it a little less expensive this time, because we know how to do it. We've done it once. We've kept drawings and procedures in place so that we could rebuild it. The concept of the Mars program for MSL and the sky crane technique has always been that it would be the workhorse of the future. So we've always intended the ability to rebuild and refly the descent stage, the rover, or some elements of that. We will spend plenty of time with the stakeholders who, as you say, hold the purse strings, and discuss with them what's next, and what we should do next and how we ought to go about it. What we lose is incredible if we don't do it again, though. Getting to the surface of Mars is unlike any other feat that we do, I believe, in planetary exploration. It's very challenging. The capabilities that we've developed of the guys you see sitting here and many guys and gals sitting behind them to do these types of things has been developed over a decade and a half, 2 decades. I think the last thing the nation can afford is to have the gap between Viking and Pathfinder that we had. It's a critical skill. It's a core competency of this country. We are happy to help, as we've offered to the Europeans, to help others figure out how to get to the surface. The science is on the surface, and the science of Mars is absolutely crucial. I should say the science at Mars is absolutely crucial to key questions in planetary science. Are we alone? The evolution of that planet from a warm, wet past to the dry planet that it is now, and the accessibility, 26-month availability, and the fact we can actually get to the surface and remain there for extended periods, either robotically or someday with humans, is something you can't do anywhere else in the solar system either. So if we lose the capabilities that we've been building from Pathfinder to Spirit and Opportunity and now to MSL, it would be hard to rebuild. It would take years to rebuild, so we don't want to lose it. That's why I think not only is the science on the surface, but you got to maintain the skill set to be able to access the surface.
Okay, we're going to the front row on this side.
Mark Kaufman with the Washington Post and National Geographic. 2 questions. Again, going back to what we tell our editors, if Odyssey does not roll properly, could you just walk us through the time frame that occurs then, in terms of when you would be getting the information that you have landed? And the second thing, Adam, you referred to Curiosity as she. Is that the norm? Is that what we shall be doing in the future?
Curiosity seems to be a better name for a she. She seems like a she. Yes. Yeah, there's also a tradition of boats and craft being feminine. Actually, Doug, if I'm...
No, go ahead.
So we have 2 different methods of communicating, 2 different frequency bands in which Curiosity is telemetering information back to Earth. One is in the UHF band through the orbiters, Mars Reconnaissance Orbiter and Odyssey. Odyssey is doing the bent pipe and coming straight back to Earth, so we get that in real time. Mars Reconnaissance Orbiter is just recording that information for playback a few hours later. But while she's doing that in the UHF, in the X-band, she's sending signals, much more discrete semaphores, little tones that are coded that say, now I'm doing this, or now I've seen this condition, and so forth. And she will be doing that the whole time. And she does that direct to Earth. Now, it ends up being before we get to the surface, Earth will set at our landing site. And so about the time we're on the parachute, late when we're on the parachute, we will no longer get those direct-to-Earth semaphores. So if Odyssey doesn't make the roll, or we can't link up Odyssey for whatever reason it might be, we won't have that real-time link in the UHF, which is very high-rate telemetry, lots of numbers, lots of great details. We won't have that, but we will have these well-chosen tones and signals from Curiosity all the way until she's on the parachute. At that point, we'd lose contact with her, and it would be probably about 8 hours later, because, again, if Odyssey is not speaking to us, or we somehow don't have the link through Odyssey, MRO will send down this recorded data, but it's not decoded like it is in the path that comes through Odyssey. It's just recorded in real time. That whole recording is sent back down to Earth, and then it gets to here, and we have to do some processing on it to decode it. And so about 8 hours after landing or so, we would have a decoded version of the Mars Reconnaissance Orbiter data to help us understand.
So if Odyssey is out of the picture, then we won't get a final answer that it landed for 8 hours, roughly?
That's correct, we might not.
So can I, if you
Yes.
don't mind,
Yeah.
very high level, we have, I think it's four
It's four.
assets, right? It's four
Yes.
assets. Odyssey, MRO, Mars Express, Deep Space Network, Earth, right? The only one that sees this through the entire process is Odyssey. And so Odyssey and Deep Space Network are the only ones that get it real time, that we get it real time, okay? The other two record, and we'll get it hours later. So think about it that way. Four assets, only one sees the whole process to touchdown real time. And by the way, if we can call an aircraft carrier a feminine gender, I think we can handle that with a rover.
I might also add, we have a video that's posted to the JPL homepage, I know it's there right now, that tries to explain to you in 2 minutes exactly what all these different communication paths are and what the different scenarios are. So if you go to jpl.nasa.gov, you can watch that and see if that helps explain it as well. I had a question over here, and then we'll go back up to the front of the room.
Burkhard Bilgo, The New Yorker. For Doug, just can you give me a little more detail about what happened to Odyssey a few weeks ago? You're saying that didn't give you much control over rolling it.
Sure.
Yeah.
Sure. A spacecraft is managed through thrusters, propulsion, as well as momentum wheels and reaction wheels. So to point and stabilize a spacecraft, you basically carry a level of momentum, and there's large, heavy wheels that spin, and they're set at different angles inside the spacecraft, so you cover all three axes to control the spacecraft. And by changing wheel speeds, you change the momentum of the spacecraft, and you can turn it and point it. So that's three wheels, right, in the three main axes. There's a fourth wheel that's called a skew wheel, and the reason it's called skew is because it's set off at an angle, because it's a contingency wheel, let's say. So if you lose one of the three main momentum wheels, then you utilize the skew wheel, and it's set at an angle so that no matter which one of the other three you lose, it imparts momentum in that lost direction. But the compromise to that is you can't impart as much momentum because you don't have it exactly aligned on the axis you want it on. That wheel hadn't been even turned on for 10 years. We don't fly on that wheel. We fly on the main three wheels. So we all kind of took a pretty deep breath when we lost a reaction wheel on Odyssey just 5 or 6 weeks before entry of MSL. That was pretty scary. The team did a wonderful job of saying, okay, we can't use this wheel that failed, and we'll use the skew wheel, but you have to kind of relearn how the spacecraft works. So the first time they tried to move the spacecraft, They realized that they can't move it in the same way they did before, and actually the wheel saturated is what they call it. So it ran up to its full speed, trying to handle the momentum in the turn, and it couldn't do it, and we went to safe mode, and we went, okay, now what? So we went back and re-looked at all the parameters, readjusted things, and so it's a learning process. You operate something for 10 or 11 years. You know, if you're driving your car and you've got it for 10 or 11 years and your air conditioning goes out after 10 or 11 years, you kind of have to think about a different way to drive your car. You got to roll the windows down now, right, or else you suffocate. So it's just a new way of doing business. There's things in there that leave us a little less confident than we had before. But it's been going great for weeks now, so the team's done a good job with it. So I think we're okay. I do. I think we'll be okay with this. But there's always that potential.
All right. Okay, we'll go ahead. We've got time really just for a couple more questions. Go ahead, please.
Hi. You said you're going to have to rely on 3 different signals to confirm touchdown. And I'd like to understand what's going to happen if you don't receive one of them. Is it possible you're going to have to wait for a couple of hours to confirm touchdown, even in the possibility the rover landed safely?
Yes, that's exactly correct. We won't say we're done until we've confirmed that we're done, and we want all 3 of those signals to confirm that.
Okay, right in front.
Hi, it's Craig Kovalt with America Space. For Doug, what level of interface is there with the White House? Will they be simply tied to NASA television, or is there an OSTP rep here with you?
I hope they're tied to the television. That would be great. And they very well may be. But actually, Dr. Holdren, the President's Science Advisor, will be here. So that's a pretty tight tie, pretty direct.
Scott Gold from the LA Times, one more time. Can you talk about, over the course of today, a little bit more of when you might start to get some clues as to where you're headed in the ellipse?
That's you guys.
I don't, you mean in the ellipse in the ground, the landing ellipse? That doesn't depend so much on where we enter, so we will not have any information. I mean, it may change by a few hundred yards at much, but the dispersion in the ground is bigger, is in the order of 10 miles. So it will depend a lot on other things, and Adam knows more about that, but including the atmosphere of Mars. So how the parachute behaves and which direction the winds are blowing. Adam, you want to say anything else?
Yes. So over the course of the rest of today, we will see if the navigation point moves around a little bit, because we're starting to see the effects of Mars gravity, and they become very, very strong. That motion in the navigation point is why we hold open this opportunity for, we call it EPU4, EDL parameter update 4. And we take those last assessments of the orbital dynamics of where we are with respect to the top of Mars, and we do that 6 hours out. So later this afternoon, we'll have that discussion. If we see a motion, if there's a lot of motion in that point, we don't need to correct that point. There's no TCM necessary, no correction necessary, but we may choose to update Curiosity's knowledge of her state. We also may choose to not to. And if we don't, then we will know at that time that she has a knowledge error, and we can expect to see that knowledge error represented on the ground. Currently, it's a stone's throw, small and inconsequential. We may choose to let something larger go, because if her ellipse is going to move a little bit, and it moves in a safe direction, we may choose just not to touch the spacecraft. The remainder, that's sort of the average of the ellipse. How big the ellipse is, where we land inside that ellipse, we won't know until a few hours after landing.
Okay, we have to end right now. I know there are more questions in the room, and even with the NASA social participants, but hopefully you can come up to them afterwards and ask more questions. I have a few things to go over concerning the rest of today. We have a chat later this afternoon at 3 p.m. Pacific time with NASA Associate Administrator John Grunsfeld and JPL Director Dr. Charles Alachi to discuss the Science Mission Directorate and robotic exploration. We are back at 8:30 tonight to begin commentary. We'll have a special half hour devoted to education and outreach with landing commentary starting at 9 p.m. Pacific time, midnight on the East Coast, and of course landing scheduled for 10:31 p.m. on the West Coast and 1:31 a.m. on the East Coast. We have a post-landing briefing will be held no earlier than 11:15 p.m. Pacific time. That will be based on how soon we get those signals back, and we'll be keeping you updated on exactly when we'll start that news conference. And for all information and many, many resources on this mission, please go to www.nasa.gov/Mars. Thank you so much for joining us today, and we will be talking to you later tonight. Thank you.
Curiosity is getting ready to make a grand entrance. The largest rover ever sent to another planet will touch down in the middle of the night after a spectacular entry into the Martian atmosphere and descent to the surface.
And liftoff of the Atlas V with Curiosity.
Curiosity made a picture-perfect launch in November 2011. And now, after more than 8 months and 350 million miles, it's time to get down to business. But first, Curiosity must get down to that surface safely. When she arrives at Mars, Curiosity has 7 minutes to go from 13,000 miles an hour to a soft landing. These so-called 7 minutes of terror encompass a sequence of steps that we cannot control or even witness in real time, because signals take 14 minutes to reach Earth from Mars. Curiosity's heat shield, burning at nearly 3,000 degrees Fahrenheit, will protect the rover as it slows down rapidly. On the way down, the spacecraft fires thrusters to stay on target for Gale Crater. Then, at 1,000 miles per hour, the chute opens, slowing the spacecraft below the speed of sound. Next, the heat shield is jettisoned, and Curiosity begins looking for the surface with landing radar that lets onboard computers know how far it is above the ground. About 5 minutes into entry, the spacecraft is moving 200 miles per hour and is about a mile up. The descent stage, with Curiosity fastened underneath, tucked, drops from the parachute, fires up its landing engines, and slows the system to a near stop. Curiosity first gets to stretch her legs at approximately 2 miles per hour, about 60 feet above the ground. With wheels deployed, Curiosity is lowered on a sky crane to the surface. After touchdown, the sky crane's work is done, and it cuts loose to fly a safe distance away from our newest rover on Mars. In a few days, as Curiosity stands up her mast, she will give us our first close-up of Gale Crater, an impact crater 96 miles wide with a 3-mile-high mountain at its center. The crater's rock layers were laid down and then eroded, showing us a cross-section of Mars's history. Liquid water was necessary to form the geology we've seen from orbit, and that makes Gale Crater a great place to look for evidence of places that could have once harbored life. During her 2 Earth-year primary mission, Curiosity will tell us about Mars's geology, weather, and current radiation levels, which are key to sending humans there someday. The rover's laser will examine rocks and help find places to take samples for the onboard chemistry lab that can identify minerals and organic materials, the building blocks of life. This nuclear-powered 1-ton rover will take us ever closer to examining deep layers of history, and perhaps closer to an answer to the ancient question, was there ever life on Mars?